Good morning and Assalamualaikum warahmatullahi wabarakatuh. Inshallah, we
Waalaikumsalam
will start
warahmatullahi
our session
wabarakatuh.
now. Okay. I'm your host and chair today. I'm Lutfi Abdul Latif, and we have here many friends around in this session. This session is also being broadcast live on our Facebook page. So some will be joining us in WebEx, and some others will be looking at the presentations on our Facebook page. Right. Before we proceed, can I request that everybody switch your camera, your microphones on off, so that we will not have any interruptions during the presentation. To start off, in order to grace this session, I would like to call upon our engineer Abdul Basit Abdul Rahman, to recite the prayers.
Bismillahirrahmanirrahim. Alhamdulillahi Rabbil Alamin. Wassalatu wassalamu ala asrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. All praise is due to the Almighty Allah, the cherisher and the sustainer of the world. May the peace and mercy of Allah be upon His Prophet Muhammad, his family, companion, and followers. Ya Allah, Ya Rahim, with your mercy and protection, we are able to gather here at this visual event, the first international seminar on aeronautics and energy 2021. We truly honored to host this occasion organized by Aeronautics Laboratory University Technology Malaysia in conjunction with its 20th anniversary in operation. Give us endless blessings for our ceremony today, as well as for the proceedings of this conference. Ya Zal Judi wal Ikram, in this inaugural conference, we humbly pray to you, Allah, the Almighty, to increase us in knowledge, in focusing the research and development in aeronautics and energy. Let this knowledge serve your cause in a way that you accept, and let it benefit humanity. Ya Allah, make our gathering here a blessed one, and our dispersion thereafter a guided and protected one. And make not any among us a wretched or deprived one. Ya Allah, make easy for us every difficult thing with your special favor and kindness. For it is easy for you to make every difficult thing easy. Allahumma ij'al jam'an haza jam'an marhuma wa tafarruquna min ba'dihi tafarruqa ma'suma wa la taj'al lahumma fina wa la Allahumma fina wa la ma'ana wa la man yatba'una shaqiyan wa la matruda wa la mahruma. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azaban nar. Wa sallallahu ala sayyidina Muhammad wa ala alihi wa sahbihi wa sallam. Walhamdulillahi rabbil alamin.
Amin.
Thank you very much, Engineer Abdul Basit, for the recitation of the dua. I would like to remind everyone again that please register your attendance in the link given in the chat. So if you open the chat in the right side, please fill in your attendance in the chat so that we can have a record of the attendance. Right. Without further ado, I think I would like to invite Engineer Dr. Shabuddin bin Mat, the Director of Aeronautics Laboratory, to begin his welcoming speech.
Assalamualaikum and greeting to all. Thank you, Mr. Chairman. Okay, Associate Professor Ainul Lutfi Abdul Latif. So yang berusaha Profesor Dr. Rosli bin Alias, Deputy Vice Chancellor Research and Innovation. Yang berusaha Profesor Dr. T.S. Ruzaidi Abdul Rahim, Dean of Engineering, UTM. Yang berusaha Profesor Engineer Dr. Abu Samah bin Muhammad Supaat, Chair Innovative Engineering Research Alliance. Yang berusaha Associate Professor Engineer Dr. Zaini bin Ahmad, Chair School of Mechanical Engineering. Yang berusaha Profesor Engineer Dr. Pakarudin bin Muhammad Samin, Director of Aeronautics, Automotive and Ocean Engineering. Yang berusaha Associate Professor Dr. Muhammad Farid bin Muhammad Said, Director Institute for Vehicle Engineering, Vehicle System and Engineering, IVES, UTM. Distinguished guests, keynote speakers, senior officers, participants, ladies and gentlemen. Okay, it is my pleasure today to welcome all of you to the first international seminar on aeronautics energy that organized by our lab, UTM Aerolab, School of Mechanical Engineering, okay, and Institute for Vehicles and System Engineering. But unfortunately, we have to organize it virtually this year. We do hope that we can do the face-to-face conference if the situation allows next year. So I would like to sincerely acknowledge, okay, the top-level management of UTM for great support and encouragement for us to organize this conference. A major goal of this seminar is to bring the academic scientists, engineers in aeronautics, energy, and related field together for us to exchange and share the experience and research together. Actually, this seminar is also held in conjunction with UTM Aerolab 20 years anniversary celebration. So the construction of UTM Aerolab was started in 1999 and it was completed by the year 2002. It was about 20 years ago. We know that, okay, each other. We know that aeronautical and energy research is a small family community. Okay, we are a very small community, which is we know each other. So within 3 months, contacting people's friends around the world, we managed to get around 45 papers from local and international colleagues in our field. From local university, we receive papers from our colleagues and friends from our university, of course, friends from University Putra Malaysia, University Technology Mara Malaysia, University of Malaya, National Defence University, okay, UPNM, International Islamic University, Polytechnic Banting, UCSI University, City University Malaysia, and many more. Your contribution to this seminar is very much appreciated. For international, we receive papers from our main colleagues, okay, in Indonesia Wind Tunnel, National Laboratory for Aerodynamics, Aeroelastic, and Aeroacoustic Technology, BPPT, based in Serpong, Jakarta. So actually 20 years ago, UTM get advice from our big brother there during the design stage of UTM Aerolab. It's again, your contribution is very, very much appreciated for us. One of the key speakers today will summarize his experience working with us. So we also received a paper from Sudan University of Science and Technology, University of Khartoum, Southampton University, UK, from Nigeria Air Force Institute of Technology, Ahmadu Bello University, from UAE, from National Cheng Kung University, Taiwan, from India, Hindustan Institute of Technology, Science, Madras Institute of Technology, and many more. To friends and colleagues, okay, again and again, your contribution is very much appreciated, okay? So ISAE promise, okay?
Dr. Shabuddin, your camera is being covered by your paper.
Okay. ISAE promise to be both simulating and informating with a wonderful array of invited key speakers from all over the world. Delegate will also have a wide range of sessions to attend. So I would like to express gratitude, okay, to our keynote speakers today. We will have Professor Josh Barakos from UK, Professor Anton Adibroto from Indonesia, Professor Miao Jinjun from Taiwan, and Professor Tanya Gairazu from India. Unfortunately, Professor Dr. Gary Armstrong from Canada cannot join this seminar today because due to his health problem. Okay, he sent regards to everybody. So we also, okay, so we also like to thank the organizing members, okay, the members of aeronautics panels in UTM, administrative staff from School of Mechanicals, and also Institute for Vehicle System. I wish all attendees of ISAE will enjoy a scientific virtual gathering. We look forward to seeing you again next year, face to face in ISAE 2020. If the situation allow us, okay? We in Aerolab, we work harder in order to make sure that ISAE will become UTM branding conference in the future. That is my promise. My bosses all are here, okay? Wish that, thank you very much. Assalamualaikum, and over to you, Mr. Chairman.
Okay, thank you very much, Dr. Shabuddin, for the welcoming speech and also the introduction to ISAE, and the fact that this conference is being conducted in conjunction with the 20th anniversary of Aerolab. Without further ado, I would like to invite Professor Dr. Muhammad Rosli bin Muhammad Ilyas, the Deputy Vice Chancellor, Research and Innovation, University Technology Malaysia, to officiate the opening of the seminar. Please, thank you.
Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Wassalatu wassalamu ala asyrafil anbiya wa mursalin wa ala alihi wa sahbihi ajma'in. Assalamualaikum warahmatullahi wabarakatuh. And greeting to all. A very good morning to Yang Berusaha Profesor Teknologis Dr. Ruzairi bin Abdul Rahim, Dean Faculty of Engineering, University Technology Malaysia. Yang Berusaha Profesor Art Engineer Dr. Abu Samah bin Muhammad Sufaat, Chair Innovative Engineering Research Alliance UTM. Yang Berusaha Associate Professor Engineer Dr. Zaini bin Ahmad, Chair School of Mechanical Engineering University Technology Malaysia. Yang Berusaha Associate Professor Dr. Muhammad Farid bin Muhammad Said, Director Institute for Vehicle System and Engineering IBES UTM. Yang Berusaha IR Dr. Shabuddin bin Mat, Conference Chair of ISAE 2021. Distinguished guests, keynote speakers, senior officials, participants, ladies and gentlemen. On behalf of the organizing committee, we are honored to welcome all participants to the first International Seminar on Aeronautics and Energy, ISAE 2021. This conference is organized by UTM Aeronautics Panel in collaboration with Institute for Vehicle System and Engineering, University Technology Malaysia. The main objective of this conference is to provide an international platform to to share the current state of research in aeronautics and energy. It is hoped that this seminar would create diverse opportunities in networking as well as knowledge sharing for future collaboration. A total of 45 papers have been submitted to this seminar. We are also incredibly grateful to have 10 keynote talks, all aimed at sharing knowledge and to generate fruitful discussion. The esteemed keynote speakers will share their experiences in several key areas in aeronautics and energy. We would like to express our sincere appreciation to our keynote speakers, Professor Dr. Anton Adibroto, Advisor to Indonesian President and Director PT Regio Aviasi Industri, Professor George N. Barakus from University of Glasgow, Scotland, Professor Jun Ji Miao from National Cheng Kung University, Taiwan, and Professor S. Tanya Gyarasu from Madras Institute of Technology, India. Other speakers include the respectful former head of Aerolab IR Muhammad Hay Muhammad, now the Vice President of the Institute of Engineer Malaysia IEM, Professor Dr. Muhammad Nazri bin Muhammad Jaafar, Professor Engineer Dr. Suhaimi bin Mansur, Professor Engineer Dr. Wan Khairuddin bin Wan Ali, and the current Director of Aerolab, Engineer Dr. Shabuddin bin Mat. The seminar is also held in conjunction with the 20th anniversary of the establishment of UTM Aeronautics Laboratory, UTM Aerolab. UTM Aerolab, operating since 2001, has achieved many success in research, training and consultancy. As a testament to this success, it has been recognized as a University Center of Excellence Research Center starting 3rd December 2020. Aerolab is a world-class research center for conducting laboratory testing and consultancy services in the fields of aeronautics and aerodynamics. It provides education and training of undergraduate engineers in a variety of aerospace fields, providing facility to foster postgraduate industrial research in aerospace and related fields, and offering aerodynamic testing services to industry. Aerolab's initiative to become a member of Subsonic Aerodynamic Testing Association, SATA, in 2022 has become an important milestone in its effort to be acknowledged internationally. SATA is an exclusive by invitation only club of about 80 renowned wind tunnels around the world, including NASA, Airbus, Boeing, BMW, and JAXA, Japan. The heart of the laboratory is the state-of-the-art subsonic wind tunnel facility, which is comparable to the best in the world in terms of flow quality. The wind tunnel has 1.5 meter height by 2.0 meter width by 5.8 meter length. Removable test section with a top wind speed of 80 miles per second. Also, other facilities under UTM Aerolab include a low-speed industrial wind tunnel, blower tunnel, propulsion laboratory, avionics and instrumentation laboratory, flight dynamics laboratory, UAV laboratory and hangar, aircraft design studio, aircraft structures laboratory and machine shop. Lastly, we do hope that everyone will find this seminar to be engaging and fruitful. This is the first event for ISAE 2021 and we are targeting to organize it annually. Thank you very much for supporting us. Thank you. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Prof. Muhammad Rosli, for the officiating address. Before we start our session, can everybody switch on your camera so that we record this session before we start, so that we see we take a snapshot of the attendance. Okay, smile again. Right, thank you very much for your cooperation and your smile. Okay, again, I would like to remind everybody, we will have 2 sessions this morning, keynote session 1 and keynote session 2, which will be conducted via this particular WebEx address. And then we have 5 parallel sessions in the afternoon, which will be conducted at 5 different addresses. So after we have finished the 2 morning sessions, everybody is invited to connect to the respective addresses for attending the parallel sessions. The addresses will be given later, but have been also been sent to you via WhatsApp and via email, I believe. Aside from the session via WebEx, we also broadcast these presentations live on our Aerolab Facebook. So maybe some others will be attending there too. As I said just now, we are amongst familiar faces, colleagues and friends who have been very close. So we'll not be conducting this session very formally, but at the same time, we'll try to have the session in an organized manner. So I would like to request again, just to remind everybody to switch off your microphones during the presentation so as not to interrupt or disturb the presentations. The presentation for each keynote speaker will be about 20 minutes, and then we'll have about 10 minutes of question and answer, so that the panelists will be able to answer or respond to your questions with regards to his presentation. We have here for the first keynote session, we've got Professor George Barakos. Hi, Josh. You there? Right. Thanks very much. Professor Anton Adibroto. Anton. Professor Miao, I see Prof. Miao just now.
Yes, I'm here. I'm here. Yes.
Okay, thank you very much. And Prof. Tanya Gaya Rasu. Is Prof. Tanya around? Okay, maybe he'll join later.
We will
Right.
join later.
Without further ado, I will give the first slot to Prof. George Barakos, who is staying. Thank you very much, Prof. Barakos, for coming up very late. I understand it's very late there for you in Scotland. So we'll give you the first session so that you will not be dragged to the morning. So I hand over the session to you, Prof. George Barakos.
Okay. Okay, so good morning, everyone. I'll try to share my screen, see if this works, and hopefully, right. Okay. So I think, I hope you can all see my screen now. And
yes, you can see.
Perfect. So I'll make a start. So first of all, it is a special pleasure presenting to your event here. And I have to say that about 15 years ago, I was visiting UTM and made the presentation about rotorcraft at the time. So I hope that with this presentation, we'll see that things have changed over 15 years rather than things staying stationary. I would like to start by acknowledging all the companies and organizations, the logos of which you see here, as well as my collaborators for a long time, Drs. Woodgate, Style, Fitzgibbon, Higgins, and Chirico, who contribute to the work we are doing in our laboratory. Today, I will talk about some recent progress in rotary wing simulation. Okay, we know about rotary wings. We have helicopter rotors. They are everywhere. We also know that a rotary wing is a propeller, and we use them in various aircraft these days, turboprop aircraft, general aviation aircraft. Propellers are everywhere. But at the same time, rotary wings include the blades of wind turbines, and because of the efficiency of this particular type of wing, we have them really at the core of unconventional rotorcraft, new configurations that we see actually being tested recently, from compound rotorcraft to tilt rotors. And rotors and rotary wings are at the core of new designs for autonomous aerial systems, personal flying machines, and all these wonderful things that you see flying now on our skies being tested, aiming for giving each one of us the flying car of the future. One thing I would say is that since the last time we talked at UTM, at that time we're mainly focusing on analyzing an isolated rotor or a helicopter. And we were just at the stage where we could do that. We had validated data from wind tunnels. We could really make sure that our simulations are getting to be correct. In this lecture, we will focus on new directions. I don't think I will have the time to touch on everything, but I would like to cover acoustics and perhaps a little bit of shape optimization. So how do we really design these wings? Of course, these topics that I have selected for this lecture are not the only topics. Of course, you can see in this slide here that we have several active areas of research in rotary wings. I highlighted in red some that are really hot topics at the moment. They like direct noise prediction or simulation of complete helicopters doing maneuvers. And so what I will present is just what is allowed in the limitations of time, not everything that is currently happening in rotary wings. Okay, the core of everything we do at the University of Glasgow is the helicopter multi-block tool. This is a system of computer codes. They are all computational fluid dynamics codes, and they have several characteristics you can read here. But what is important is that it is not a single tool. I'll explain what I mean using this slide here. Our simulation method includes a core CFD solver. This manages grids, frames of reference, all sorts of things. Nevertheless, an isolated CFD method is not really very useful if you want to simulate a complete configuration. For example, we have dedicated modules for acoustics. We have dedicated modules that allow us to trim and maneuver aircraft. So we have like a flight mechanics, if you wish, module that is driven by the aerodynamics of the CFD method. We have multi-body dynamics methods that are very useful when it comes to doing simulations of mechanisms like the articulated rotors or semi-rigid rotors and the like. We have methods to analyze structures. And for certain problems, we need to interface the core solver with methods like the lattice-Boltzmann method or smooth-pattern hydrodynamics and other tools that are better suited for applications that are requiring perhaps a different approach than a conventional CFD solver. Okay, this code is very accurate. I will not tell you about all the detailed validations we've carried out and the work that has been carried out in the past, but I will mention here the results from a workshop that is still taking place as part of the AAA events, which is dedicated to the prediction of the hover performance of rotors. So this particular exercise includes the hover prediction of the S-76 helicopter blade in rotor, and the results from our solver were seen as some perhaps of the most accurate, if not the most accurate. And I'll show you here a plot that it was done by a colleague, not by myself, showing here the RMS error across a range of conditions between our solver and other tools that are available at the time. We are one of the best performing methods, very, very low deviation, and we use very few grid points in comparison to others that use a lot of grid points in the CFD grid just for a little bit more accuracy. So the method is, this is one example, the method is fairly well validated. It is to the point here in this slide is that we are now at the point where we can predict with our methods the performance of rotary wings very, very close to what can be measured. Actually, if you perform different experiments, different flight tests for helicopter rotors, for propellers, for all this, you may find out that the scatter between these various experiments is actually more than the error with CFD methods. So we are really reaching the point where we can use these methods for design, and I will come back to this point, how we can use these methods for design. Okay, it is important to know that noise is a hot topic at the moment. We want our aircraft to have very low emissions, and this includes noise emissions. Whenever you buy a ticket for a flight, at least in the UK, you look at this rating here. You want to know how you are doing in terms of noise and how you are doing in terms of CO2 emissions to the environment. So noise is important. It is very difficult, though, to predict noise. To predict noise means that not only you have to capture the flow very accurately, but you have to preserve tiny little acoustic waves that live on top of your flow solution. This is the reason careful wind tunnel studies have been conducted where acoustics has been measured, and provided you use high resolution methods, you can actually capture tonal and some of the broadband noise that you will have in a typical installation of, let's say, a propeller in front of a wing. If confidence is there for this kind of flow, the question is, what can we do with it? Well, one of the things you can do is you can start rethinking whether it's worth changing the way propellers are installed in aircraft. For the ones of you who are not into rotary wings and all this, most of the aircraft, the twin engine turboprops, for example, that we see here, follow the configuration you see on this top diagram here. So basically, if you sit at the pilot's seat, you see the propellers co-rotating, going from the top of the windscreen to your right. It doesn't mean that there are reasons why this is a good configuration, but for noise purposes, having other configurations, it is also possible. I mentioned that it is difficult to do acoustics. You need not only to model complete surfaces, because surfaces reflect acoustic waves. You have to model the rotary wings in detail, and you are in the many million point computations when you do these types of analysis. Of course, you capture the aerodynamics. You can see here different configurations, co-rotating, top in, top out rotations for propellers giving different wakes. But what matters is not only the flow field and the performance of the propeller, but it is also important to have good noise predictions. You can see the loading on the wing affected, of course, by the propellers. You can see here the effect of the propeller on the wing load, and of course, the interaction with the wing creates unequal loading around the azimuth on the propeller, and this is important for acoustics as well. If you look at the acoustic flow field generated here, you will see that the areas where the propellers interact with the wing are strong sources of noise. We have real changes in the predicted noise, and of course near the propeller there is noise radiated. You can look at the complete aircraft. You can look at what is happening near the body, where we have strong interaction of the wakes with the wing, producing strong noise, and also interaction with the fuselage, generating, if you wish, noisy spots in the fuselage too. Interrogating the solution, one sees that it is not only the wing, but the fuselage that also has strong acoustic interference. And if you take the ellipsoid shape of the fuselage and you plot the sound pressure level around, you will see that according to where you look around the azimuth, you have different levels of noise. I can see you here different, if you wish, effects around the excuse me. So the calculation is detailed enough to reveal the interactions, but also to show how noise will be radiated away from the aircraft and behind the aircraft too. Now, measuring the acoustic characteristics of the fuselage, one can really find a way to generate not only the noise outside the aircraft, but inside the aircraft, which is also very important because of passenger comfort as well. So this was done here for an aircraft that we measured as part of one of our projects, and using these measurements, one could correct the external aerodynamics from the CFD for internal noise. And so if you unfold the fuselage, you can actually see the hot spots of noise and how these are transferred inside for different configurations. And clearly, this configuration here appears to be far more quiet when it comes to passenger noise. I don't know if the noise will be able to be played through, but I will attempt to play you what a passenger would experience inside this. Yes, I think the noise is not transferred through, which is a pity because I have a few synthetic fields of noise generated through CFD. So, which is quite interesting because we are now at the point where we can reconstruct the acoustic signature of an aircraft using the detailed computations. Another thing that you can do, of course, if you are confident that your predictions are reliable, is that you can get into tricks like syncophasing, where you are trying to change a little bit the phase angle of the blades and generate the acoustic field of the fuselage. This is an optimization problem to find the correct phase angle on the blades, but it is tractable because these computations can be performed on large-scale parallel computers. And there is an effect. Indeed, by changing the phase, you can reduce the noise inside the fuselage. For example, we can have substantial reductions up to 6 decibels in certain frequencies by simply phasing the propellers differently. And this is a change that is very easy to implement. Many aircraft already have a synchrophasing mechanism. What we do with this is, honestly, we're trying to reconstruct the details of the noise. So this is an example from an old experimental investigation of rotorcraft acoustics, the famous HART-2 experiment. And what we've done, having validated our methods against this, we can reconstruct the noise that we have from this kind of vehicles. I will play one clip here of a reconstructed noise. Hopefully this will come across, I'm not sure. So this is the reconstructed noise that you have as a result of blade vortex interactions that happening on a helicopter rotor. And at this stage, whenever we have time for these presentations, I ask the audience to really select which of the 5 recordings you see here is real, is recording from an aircraft, and which one is generated using computational acoustics. For example, if
We cannot hear it, Prof. Baragas.
Yes, I'm not sure why I can hear it clearly here.
I think it's something to do with the settings for the WebEx. Okay, no problem.
I can see if I'll see if there is anything obvious here I can fix. More options. Yeah. Yes. Right.
It's got to do with the video option.
In this case, I will skip it because we don't have also a lot of time as well. So I will show you a more modern example. This is a work we recently did for an electric vertical takeoff landing vehicle. This is a complex vehicle with tiltable wings, with propellers, with rotors. It's a very complex aircraft. You can see here the configuration. We use high quality overset grids to mimic the relative motions. And I'll show you here, for example, the variation in thrust between different blades for this vehicle in different phases of flight. So there are many blades there, many wings, many propellers, and apart from the noise that these lifting surfaces generate, you also have reflections of acoustic waves on the wings, on the fuselage. And so it is not really the performance metrics that we see here are okay, but what is important is to see the acoustics. You can see here how active this flow field is. For example, we have here lifting surfaces, and what is happening is that we see that the acoustic waves are really reflected on any surface they are projected on. So this generates hotspots of noise. I think I have here the relative scale because this is a real aircraft and we could not show the full scale of it, but you can appreciate that it can be quite a noisy environment. Different configurations of flight, forward flight, they have different acoustic predictions. But what we have done is that again we tried to phase the different propellers so that we can have a better acoustic environment in the cabin. So through an optimization method, we found out that a small change of phase angles can substantially improve the acoustics of the fuselage. This is the performance. This is perhaps not very important. The synchrophasing has no effect on the performance of the aircraft. But you can see here that through the synchrophasing, the area near the cockpit has now much lower acoustics than what we had before. And this reduction is substantial because this is this is a real aircraft. There is a restriction in presenting the exact decibels, but there is a substantial reduction in noise in the fuselage, and this is important for comfort, for passenger comfort. Okay, very briefly, because we're running out of time, not only acoustics is important, but we are now asking the computers to tell us the shape of things that will fly. So can you really ask a computer to design a rotary wing for a helicopter? That's quite an interesting question. Engineers take time to do these things, but most of the times nowadays we want to rely on computers to do detailed optimization work. In recent years, there have been several advanced platforms in helicopters, and all of them aim to really reduce acoustics and increase performance. So what methods do we use for this? Most of the times, the optimization efforts today are what we call brute force methods. People do a lot of calculations on different shapes, and try to come up with an optimal shape using some sort of model, maybe a neural network or maybe some curve fitting. In general, this requires thousands of computations, and nobody has really done a full optimization of the shape of a blade with a high fidelity CFD method. So all the works you see here are done with very little CFD. Most of them are with blade element momentum methods, these lower fidelity methods. On the other hand, if you are to use gradient-based methods, methods that use gradients of the design, the sensitivities of the design to the design variables to have accurate results, you will find out that they are not very many. So today you will find gradient-based methods for optimization of aerofoils. Not a lot of work is done in this area. And recently we've seen works on inviscid flows around rotors. In our laboratory, we've recently published the first full-scale CFD optimization of a rotor. So we want to know the optimal shape of a helicopter blade for a given particular constraints. And we do this using a gradient-based method, using an adjoint-based solver, a solver that calculates sensitivities of flow to design variables, and an optimization. A key issue here is that because rotary wings are unsteady, we cannot easily do the optimization. If your problem is steady state, there's a lot you can do, but for unsteady problems, it's very difficult to do optimization. So what we do is that we solve the Navier-Stokes equations in the frequency domain. So what we do is we really solve for modes of the flow solution, the same way the model approach is used, if you wish, in finite element techniques and all this. So what we do is that we have modes of the solution, and in a way we convert an unsteady problem to a set of steady solves. The benefits you have from this method is up to 100 times of improvement in speed. And of course, if this is combined with a method that you can do in our solver that gives you the sensitivities of every single design parameter, the shape of the wing, to the flow variables, then this unlocks the path for optimization. A snapshot of our optimizer is shown here. We have algorithms that deform the CFD grid. You have the flow solver. You have the sensitivity calculation. You have a parametric representation of the rotor, and you have an optimization algorithm. So these are the key 5 ingredients of this method. Of course, this is a big calculation, but it is tractable using today's computers. I will show you here the parameterization of a blade. We can vary the chord, the twist, the aerofoils, the tip, and we have a wide range of designs we can achieve by varying few parameters here. We did this as an example. We took the AH64A blade, and we made sure that we can analyze this blade, and we wanted to see what the shape of this blade would be if you ask our solver to minimize the power required by keeping the thrust this blade generates. I will not really give you all the details of the method. We have this published, but you can see here that if you only make your blade efficient for hover, you will go from the original shape to this red shape you see here. Is a highly non-planar blade with anhedral dihedral kind of tip and a non-uniform chord distribution. Of course, you can see that the optimizer cleans the flow near the tip. There is no compressions here. It really has a very, very nice solution. One interesting thing the optimizer did in hover is that it took the strong interaction between the blade and the vortex under it and made it a much weaker interaction with a more diffused vortex. This was the first The last step of this method was to bring in, I'm finishing in 1 minute. The optimization in forward flight was similar. And I will show you here the blue shape, which is what the computer generated for this example. And the performance is really significantly improved in hover and forward flight. As summary, you have 6.5% savings in power and 6.1 counts of saving and figure of merit in hover. I realize that we're running a little bit long. It's a bit late here and I'm a bit perhaps slower than usually, but what I will do is that I'll take you to my slide showing the conclusions and the summary. It is quite important to understand that rotary wing is a growth area. Propellers may seem old-fashioned and all this, but they are really a growth topic in aerospace. We need special methods to analyze these flows, and acoustics and shape optimization are now coming together. Whenever we optimize for performance, we want to know the acoustics and vice versa. So in the near future, we will see how this combined optimization will benefit the grand challenges we have in aerospace, which are the electrification and the decarbonization of flight. All right, so I realize that I've been overrun. I'll leave it here in case there is any pressing question. Thank you.
Thank you very much, Josh, for the presentation. It's very interesting. Something which is an eye-opener for me, which is involved in another field. Right, I open the session for questions and answers. If there are any questions, please feel free to ask Josh. Any questions?
Can I ask?
Yes, please, Dr. Anton.
Yeah, thank you. Josh, you ever compare also the noise of the electric with combustions airplane? It is the noise is lower from the electric aircraft or what?
Okay, that's not a question that has a simple answer. Well, of course, engine noise can be quite low for electric engines. What is the problem is that in general, whenever you go for a little electric vehicle like the ones that I showed with the tilt wings and all this, you tend to use RPM regulation. Traditionally in aircraft engineering we change the pitch of the blades, but with electric motors it is very easy to change the rotational speed. And so now you are in the problem where you have to be very careful because not only you have to get the acoustics to be low at a given frequency and harmonics, but you have different frequencies. So the problem is far more complicated. So although you get rid of some of the engine, the core engine noise, if you are not careful, you may end up having a far more noisy aircraft. So you have more frequencies to take care of now, each one with its own harmonics. And this is perhaps the reason I think that we have to start using more computer-based optimization methods, because it's very difficult by hand or through intuition and engineering judgment and practice to get everything right. But is a topic that requires, I think, a very long discussion. What is quieter? Yes.
Right, thank you very much, Josh, for the explanation. And I really appreciate your coming tonight to give the presentation and sharing for us. Right, we move on to our next speaker, which is Prof. Dr. Anton Adibroto. Right, just a little introduction on Prof. Dr. Anton. He received his PhD from Institute of Technology, Bandung, and has got 40 years of experience in the aerospace industry. I I think I would like to mention also that Prof. Dr. Anton was our advisor together with Dr. Andi Ekasakia and Dr. Sujatin as the technical advisor for UTM Aerolab when we were planning to build the Aerolab before. So without further ado, I'd like to invite Dr. Anton to give his presentation. Dr. Anton, please.
Okay, thank you very much.
So can you see my slides? I am sharing slide from Professor Anton for Professor
Yes.
Anton.
Not yet.
No, you're showing your okay. Yes. Can you please do the presentation mode? Thank you.
So okay now? Okay,
Okay.
Prof. Over to you, Prof.
So I was invited by UTM to give some commemoration of UTM LST actually. That's why the past and future of UTM LST. Next. Four. One slide before, please.
Okay.
Next. So this. Yeah, this. The cooperation start in 1994, 1995, when the Professor Afifi come to all over the world to see the cooperations with building the wind tunnel in Malaysia. So they come to us after recommended by NLR, National Aerospace Laboratory, Mr. Yasma, to recommend us as an advisor for UTM. So afterwards, after being appointed, LGG make a several survey with the UTM team, which is chaired by Muhammad Kir and co-chaired by Pak Suhaimi. So we visited aerospace facilities in China, in Mianyang, Sichuan in 1995, and the IOLOS wind tunnel in the Toronto. IOLOS is DSMA. DSMA is the design and engineering company who made the DNW, German Dutch wind tunnel. So our tunnel in Indonesia is not designed by the IOLOS, but by the Dutch company, which is advised by NLR. So finally, the contract awarded to the IOLOS with several reasons. Next, please. So during the 1996, I think Pak Kir and Suhaimi was there for 6 months. So the hard selection of the wind tunnel made from wood or from steel or from fiber. So finally, they select all steel with the inside equipment as fan drive, fan blades, screen, underfloor external balance, data acquisition and reduction system, as well as tunnel control system. So this is the complete inside the wind tunnel who can control the speed and the quality of the flow. So this year's UTM LST is 20 years. Johor Bahru become the son of our tunnel ELST 30 years in Sepang, and the grandson of the NW 40 years, German Dutch wind tunnel in Voornhoven, Netherlands. So the quality is almost the same because we benchmark from the DNW, which is the best wind tunnel in Europe or even in the world, which 8 by 6 meters, and we are half size 4 by 3 meters, and UTM LST also another half size is 2 by 1.5 meters. Next. So you can see building the tunnel is easy. only 4 or 5 years, finished. But building the manpower is more difficult. That's why during the same time, the people at the UTM spend all over the world to learn how to make a research, doing a research in the wind tunnels, to learn how to operate, and how to learn to the maintenance. So they are also trained by the vendors for the engine, blades, screens, sections, as well as the testing itself. So you are using the underfloor external balance. Actually, that's the most modern balance that being applied by DNW. Here, I didn't say I make mistakes, but the Dutch advise us to use the overhead external balance with the wire and so on. The drag is more, sometimes more than the aircraft itself. So you have to make a lot of correction. So this kind of mistake, we don't want to repeat it in the UTM-LST. So I can say the UTM-LST is more similar using the underfloor external balance, like the same as the DNW. So we advise not to make the same mistakes, if call it mistakes, but also in terms of the operation of the changing the models, is easier to use the underfloor balance compared to the external overhead external balance. So we back to the survey with Pak Kir and Pak Suhaimi. There is a picture there in 1995, and then also going to Toronto in 1996. So of course, always the difficulties as the suppliers or vendors always they want to supply the most easy for them. They don't want to supply the more complicated one. But we as the users want to have the most useful for the operation of the tunnels, makes the maximum benefit of the tunnel that can be used not only for the aircraft, but also for the non-aeronautical testing. Next. You can see that the UTM LST has the section 2 times 1.5 meters, velocity of 80 meters per second, and the can attain Reynolds numbers 1 million. With the spatial uniformity, the variation is very variation is very low. According to the international standard, this is one of the best wind tunnel in the world. So the flow gradient also, see the changes of the what is that, temperature also very low. So you can see the some kind of test in the low speed aerodynamics as well as the CFD. CFD is actually not supplied by the IOLOS, but can use a lot of CFD that fight by all over the world, either panel method, NASTRANS, which is being used by others, Fluent as well. And you can see also the measurements, either forces, wake survey, flow field, and flow visualization as qualitative methods, and also can do several testing, 3-dimensional, half model, as well as the 2-dimensional model to attain the more higher Reynolds number. This is also the several picture that UTM LST people train at the low speed tunnel in LAGG in Serpong. Next, please. So this is a contribution from Sabudin that after completed in year 2000s, the become operational in 2001 and 2002, certified as a member of SATA, which is not easy. You have to prove some work and some quality. Your Prime Minister launched the laboratory in 2005, and the annex propulsion lab and hangar is being provided in 2008, and then you upgrade in 2020. Nowadays, up to the futures, you should target it as a center of excellence and financial sustainability. So everywhere in the world, this financial stability is not easy. Even the NW is still subsidized by government. So this kind of financial stability is not very challenging. Next. So based on the current and future scenario, you make the environmental scanning for the positioning of aero business. Then you make a strategy. You got the business plan, and you have to move forward up to your midterm target in 2024, financial sustainable. So the difficulties with wind tunnels, the test section is only once. You cannot do parallelly, always serials. The hours is only 8 hours, unless you make a 2-shift basis, or you make another wind tunnels next door, which it can do parallel. Next, please. This is the roadmap, a UTM LST to become center of excellence in the university, but also would like to have the financial sustainability. Actually, international recognition you have already, but the amount of the cooperation with the international, you should expand more. Yeah. And then phase 3 will be the new game changers on transformation challenges, which is a lot of cooperation with the computational fluid dynamics. A lot of things can be simulated outside the wind tunnels, so the wind tunnel times can be reduced. That is my prediction. Okay, next. This is the facilities you have now. You have the subsonic wind tunnel facility. You have the hangar. You also have the structure rigs, flight simulators, design, information avionics, propulsion lab, and you have also the UAV laboratory, FD laboratory, finite element methods, which is supporting the testing to become more efficient. Next, please. So this is the future project. What I can see, after crisis, that the wind tunnels in the Serpong also, there is no airplane going inside, but a lot of bridges. I think around 50 bridges in Indonesia being tested in the wind tunnels. High-rise building, not so many. Next, green building will be more come to the pictures. Disaster-resistant structures, because we have a lot of earthquake compared to Malaysia. We have the cooperation with the public works that they would like to have the lot of the testing with the disaster-resistant structures. Nowadays, we also high-speed train and mid-speed train. even MRT also being tested in the our wind tunnel by the Japanese. They use also the measuring actually the noises in the wind tunnels to predict the noises in the stations and surrounding. Pollution control also become more serious. We should simulate it in the wind tunnel. I don't know whether UTM already have the power on facility using either electric motor or a compressed air system. So this is also become more interesting to simulate this the calculation being performed by the first keynote George, which is we should have a close cooperation with him. And in Indonesia also the for the next airplane that we design, we have to consider the hybrid. This is all interesting. Hybrid combustion either with electric or with the hydrogen fuel. But according to the some studies, the hydrogen fuel is more lighter than the electric battery. Yeah. Again, the transition to turbulence, the flow visualization also important here. Wind engineering, and again, the flutter testing also create either noise or aeroelastics to the body of the airplane. I think that's all my thought, I think. So, finish.
Right. Thank you very much, Anton, for the
You're welcome.
presentation. I can now open the session for question and answers so that Dr. Anton can respond.
Okay.
Any question, please? Thank you.
May I ask a question from
Please,
JJ Miao?
Yes, Prof. Miao,
Yes,
go ahead.
Professor Anton. Yeah, very nice.
Yes, how are you?
Okay, okay. Yeah. I
Long time no
believe
see.
we met before, right? With
Yes,
Andy and
several times. Yeah, in
Professor Surya.
Taiwan, especially in Serpong. Yes.
Yes, yes, and LAGG, I visit. Yeah,
Yes.
it's also around 20 years ago. It's very impressive. Yeah, amazing facilities.
We have several
LAGG.
joint research.
Yeah, and yeah, I just learned this this histories how you transfer this technology to UTM. So may I ask the questions? Okay, how
Yes.
you mentioned about the training people. So what's anything? Okay, more is like a key here. Okay, to operate a wind tunnel and to keep it going. Okay, to the future. So what's the key you think the most important?
So, okay, thank you. In 1995, I was approached also by 1995. Yeah, Dr. Andi maybe remember.
Yes.
Correct me if I'm wrong. Korea Aerospace Research Institute want to make the same 4x3 meters, and then we are also appointed as a consultant, and then finally they make in all steels 4x3 meters in Taichung. But they also send all PhD returnee from United States come to Indonesia to be trained. So the most important thing is the experimental or wind tunnel testing is a lot of high touch problem. It's not high tech, yeah. So you have to touch, you have to make a connection, you have to make a solder something, the IC on and so on. Especially we divided into several what is that factors or qualifications. First is aerodynamicists, can be analyze the result. Second is mechanical engineers who can build the models and install the model. Third is the computer science, who can process data acquisition reduction system. And fourth is electrical engineer, who can control the tunnels, speed, and then as well as the tunnel control system, in order to have the right response for the operating the wind tunnel. So it's not only aeronautical engineering in a wind tunnel. So this kind of field has to be trained, because you cannot work alone. So the teamwork is very important. So this kind of backgrounds is needed for operating wind tunnel. That is my my experience, Professor Miao.
Yes, thank you. So yeah, related to this, since I'm doing wind tunnel experiments, well, we know this is the people involved in this wind tunnel technique, wind tunnel operation, or even experimental fluid dynamics. It is a kind of a rare species people, okay, in the world. Now
I
become
agree.
less and less people, okay, doing this wind tunnel testing, and particularly to operate such nice and big facilities, you need a team. So what do you think? Okay, you mentioned about the different expertise, okay, to become a team. So yeah, probably the question is regarding how long you think, and you know, to for these people have training and then get experience and so on. Yeah, based on your experiences.
Yes, average is 1 year.
Yeah.
Average is 1 year.
Mm-hmm.
So we send 20 people to NLR, National Aerospace Laboratory in Amsterdam, for those field. Especially for model making is 1 year. For the tunnel operation, 6 months. Data acquisitions, reduction system, also 1 year. But being back to Indonesia, still being supervised, because every testing will be different techniques being applied. So this is quite complicated actually. So it's all not always the same. So this correction method is different. It is quite complicated.
Okay,
So
but I see Josh is trying to ask a question. Josh, please.
Yes, if I may ask, I've seen in recent years a lot of wind tunnels closing down, being decommissioned, but at the same time, I've seen that people are building new facilities for acoustics. It is a very important topic, but by its nature, it requires significant changes to the wind tunnels. Is this part of your plan for the future? What is your idea on this?
Yes, we in Serpong we have the aeroacoustic facilities as well, but not as big as DNW. And we also have aeroelectricity facilities, because you call it aerodynamic, aeroelastic, and aeroacoustic. So always very close. Even small things create noise. So this is more to the environmental, getting more serious problems. So this kind of things, the same also in the future. This aeroacoustic matters is more becoming. That's why I asked you, because now in Indonesia we try to select what kind of motors or engine being used by the hybrid in the future. It is quite complicated. But when I saw your presentation, maybe we can contact you in the future to make a comparison for us, because we can cooperate on the predict what kind of selection of the engine, electric or hydrogen, or combined with the combustion engine. So this is
Yes, I mean, yes,
getting crucial. Getting crucial. Yes.
This is great. The reason I mention this is because I see acoustics as perhaps a way to keep more tunnels in operation.
Yes.
Especially, over here, we lose wind tunnels every day, but the ones that have our acoustic capability, they
Yeah.
seem to have the growth and the potential only because of the impact to the environment. Much the same way all the other things you mentioned about pollution, dispersion, and all this research into atmospheric sciences in a wind tunnel is quite important and definitely can help tunnels keep their operations and flourish in the future. Thank you.
So maybe Pak Andi
I have a
can.
question here. Can I ask a question?
Yes, Prof. Hafizi.
Yes.
May?
Hi, how are you?
Fine. How? No. Yesterday I attended a talk. By Autodesk. It seems that everything can be done virtually, from design, from testing. Will the wind tunnels one day will be replaced by all those virtual testing? You can design, not necessarily person Anton answer or anybody else can answer. But
Yeah.
it seems that with the capacity of computers nowadays and with advances in computing and all those things, it seems that most things can be done in the virtual mode, no more in the physical mode. Can anybody answer the question?
Anybody would like to respond to that?
So
Josh?
one day the wind tunnel will be replaced, but all done on computer.
I think that it is inevitable that we'll have fewer wind tunnels, but we will have better wind tunnels. The problem with the computational methods is that they always need data for validation. And unfortunately, the data we need today is different from what we needed yesterday. When I started with simple methods in computational fluid dynamics, we were happy to know the lift and drag of an aerofoil measured. Now we want to know pressure distributions and flow fields and acoustics and the details of turbulence, and we want to have time resolved measurements. So what is going to happen is that there will be more pressure on wind tunnels to increase their instrumentation,
Yeah.
their level of output. Wind tunnels will be a lot more computerized. You will need almost a supercomputer attached to the tunnel to process the data that will be gathered over a short experiment. And unfortunately, wind tunnels that don't receive the investment from government and from industry to keep up with these technologies, inevitably they will have no reason to exist. I'll say only in this example. Years ago in the UK, there was a survey, and we found out we had that about 600 wind tunnels. 600. And so you understand that we don't need all these wind tunnels. So out of these 600, maybe we need 20, 30 that are very good. That's why I was very encouraged from the previous presentation that emphasis was put on education and instrumentation, sending people abroad to develop new instrumentation techniques, combining fast data processing. This definitely will help wind tunnels stay there and produce all the great things they use. But I see a future for wind tunnels. I like wind tunnels a lot. It's just that they are very expensive now, and as a result, there will be fewer, but much better. So that's my simple answer to a complex question that you've asked. I wish I had had a more comprehensive one, but I'm not an expert in wind tunnels.
Okay, thank you.
Thank you very much, Dr. Anton, for the presentation, and Prof. Barakos and Prof. Afifi for the questions and the participation. I think we move on to our next presenter. We have Professor Miao, Gyunji Miao from NKCU, National Cheng Kung University, Taiwan. Prof. Miao received his PhD from Brown University in 1984 and is the president of Aeronautics and Astronautics Society of the Republic of China in 1998 to 1999. Prof. Miao is an expert in fluid mechanics, aerodynamics, and his work focuses on cylinders, circular cylinders, cyclist aerodynamics, PIV, delta wing configurations, and many fluid mechanics related topics. And he's also involved in the CFD. He's currently a distinguished professor at the National Cheng Kung University, Republic of China, Taiwan. So I hand over to you, 20 minutes, Prof. Miao.
Yes, can you hear me?
Yes, yes, Prof.
Yes, very much.
Okay, so can you see my presentation full screen?
Yes.
Yep.
Okay, so now I'll start my presentation. Okay, good morning. And first of all, I'd like to acknowledge the past opportunities that I have the connections with UTM, okay, through SAWE meetings, a number of SAWE meetings. I believe Rolfi and yeah, you know that we meet, yeah, we have very much enjoyable time, okay, of the meetings. SAWE means South Asia Workshop for Aerospace Engineering. Okay, it's organization consists of a number of universities, including National Cheng Kung University, UTM, and so on. Also, I'd like to acknowledge the support from the SATU. Okay, South Asia. Okay, it's also a union. Okay, organized by NCKU and a number of universities in South Asia. So today I'm going to present to you, okay, this with this title. Okay, the title is a little bit long. Yeah, the first part is the past and future research in experimental aerodynamics. Okay, and this part actually was assigned by Professor Shabuddin. Okay, and yeah, it's in the poster. In fact, I'm going to address the second part of the title, vortex interaction or leading edge configuration, which is the result, okay, we obtained recently. And later on, I will also show you how these two parts are connected, okay, to this future and the past and future research in experimental fluid dynamics. Okay, so as an introduction, okay, this illustrates the interaction of the stroke and wind vortices on a double delta wind. Okay, you can see here, okay, this on a double delta wind, okay, the vortices mainly consist of the stroke vortices, and the other one is the wind vortex. And in this result actually is a copy from a paper, okay, in the literature to illustrate how these interactions, okay, between the stroke and the wind vortices. And you can see that through this interaction, they're featuring this vortex merging, okay, this merging between stroke vortex and the wind vortex. And also it can be vortex breakdown, which is depending on the angle attack. Okay, so you can see here's two cases. One is a 19-degree alpha angle. The other one is the 22.4. So you can see that on the right-hand side, actually this vortex breakdown very clear. Okay, occur near the leading trailing edge of this wind model. Okay, so I put here as a question is regarding the effect of Reynolds number, which is I'm concerned in this study. Okay, the next one, I'd like to present you a case which is known to many people. It's a sharp leading edge vortex on the delta wind. As you can see, two nice photos, also copied from Van Dyck of album of free motion. Okay, this is the case that, okay, characteristic the leading edge vortex actually insensitive to Reynolds number, as you know. And this is evidence, the evidence reported in the literature. Okay, I also copied this from a paper, okay, quite some years ago. Okay, for delta winds, the angle attack corresponding to the onset of the vortex breakdown is non-insensitive to Reynolds number. Okay, included here, this is the plot, okay, including a number of experiments and even flight tests, the Reynolds number ranging from 10 to the 4 up to 10 to the 6. So from this plot, you can see that, okay, this, okay, onset of vortex breakdown, the angle attack actually, okay, function of the strip angle, okay, very clearly, strip angle of this delta wind configuration. On the other hand, okay, this data point actually not scattering very much, okay, with respect to Reynolds number. So this is a kind of evidence people recognize that for the delta winds, okay, sharp leading edge, okay, the characteristic of leading edge vortex quite insensitive to Reynolds number. Okay, so it's come to the present study. Well, we are concerned about Reynolds number effect on this vortex interaction, okay, on leading edge configuration. So the effect, I mean, the Reynolds number effect has been extensively studied for various flow phenomena in the past. And I believe, okay, the people talk about this, okay, continue to be an important topic for future research. Okay, so speaking of this, I think, yeah, I'd just like to point out Reynolds number effect actually related to a very fundamental issues in fluid mechanics, which is called the dynamic similarity. Okay, so we always like to have this ideal situation in experiment or numerical simulations. We like to have the same Reynolds number, okay, as the flight condition, for instance, or the real conditions. However, this is in most of cases, this is almost impossible, particularly in a wind tunnel experiment. Okay, so Reynolds number effect is always concerned by experimentalist. Okay, and I should also mention that the result I'm going to present here is published recently with my student Zhou and Chen. These two my master students. Okay, so comes to the objective of the present study. Okay, we like to study the phenomena vortex in the interaction on this configuration is selected. Okay, NASA TP 1803. I will show you later. So we'll conduct the flow visualization experiment in water channel, low speed wind tunnel, for Reynolds number over 1.5 10 to the 4 to 1.2 10 to the 5. So it's just about the range of one order of magnitude. And then we also select the case, okay, for PRV measurement for Reynolds number at 3 times 10 to the 4. Okay, so what are we going to do is to examine the result of the experiment, okay, made for angle attack, 3 angle attack, and from which we like to examine the Reynolds number effect, okay, for these 3 cases. Okay, here shows the model. Okay, we have this model configuration schematics with the dimensions indicated for our experiment. And the model was made by 3D printing. Okay, actually this is the student project. Okay, we are not really not able to make spend too much funding on these full models. So we simply just use the 3D printing. And on the right hand side, we have a photo taken in the water channel. Okay. And speaking of this model, you may refer to a paper. Yeah, it's which lists all these configurations, informations. Okay, so speaking of this water channel at our lab, okay, it's a recirculating type, and the test section, okay, is 600 millimeter by 600 millimeter in cross section, and turbulence intensity is lower than 0.7%, and the maximum velocity to 0.4 meter per second. And here I put it here is the information was provided in a master thesis of my previous student, yeah, in 2008. And here shows the information about this 2D PIV specifications. Okay, we have this laser source, okay, 5-watt laser source, and with the optics to produce the laser sheet 1 millimeter thick. Okay, you can see the photo here with the optics. And the high-speed camera, okay, with the frame rate up to 3,000 frames per second, and with the resolution, okay, 1024 by 1024 pixels. And the software, you can see here is the PIV view. And I should also mention the information provided in my student, Zhou, yeah, I mentioned it here, is one of the co-authors of the paper I mentioned. Okay, and here, this is the, also we conduct the experiment in a in open jet low speed wind tunnel. Okay, here shows the schematics of this wind tunnel, and 3D view shown here is that we have this open jet, okay, with a circular shaft, okay, 500 millimeter in diameter, and speed range from 5 to 40 meter per second, and the free stream turbulence, okay, is also around the point. I'm sorry. Okay, it's because my screen. Okay, anyway, yeah. Okay, I'd like to show you this information is given in Miss Chen, okay, just a graduate from our lab, okay, and also one of the co-author of the paper. Okay, so here comes the result of the visualization. Okay, so here I show you this start from this alpha angle 5 degree, okay, with the oil flame, okay, and the Reynolds number 1.5 10 to the 4. In the water channel, okay, here we are able to see this, identify this track vortex, okay, and also this leading edge vortex, which is associated with the wind. And in this case, you can see that the track vortex is very clearly formed, but the wind vortex is really not that clear. And at the 10 degree angle attack at the same Reynolds number, yeah, in this district visualizations, particularly to indicate that the formation development of this track vortex, which is in a consistent form, persists to the end of the trailing age. And on this photo here, you show this 10 degree Reynolds number 5.7 10 to the 4. Okay. High Reynolds number, which is made in a wind tunnel, okay, using oil film visualization. From this visualization, you can see that there's two indications of the secondary separation lines. Okay, one is associated with the track vortex. Okay, secondary separation induced by track vortex, and the other one is induced by the wind vortex. So this is a clear indication of the formation of the two vortices. Okay, about the wind. Okay. Okay, so the next one here, yeah, is concerning this alpha angle 20 degree, which is the most interesting one here. Okay, we have this in the water channel, we have this track vortex, and the wind vortex shows strong interactions near the trailing edge. Actually, call this is kind of spiraling, okay, interactions. Okay, and that's another view of using these in-depth images. Okay, you can see that in addition to this development of vortex, okay, track vortex and wind vortex, you also see there's a large scale, okay, separations form on the wind surface. Okay, by doing this, okay, we are able to make a hand sketch, okay, based on what we learned from the visualization. You can see this strike vortex, okay, it's kind of very strong, and which induce this wind vortex coiling around. And at the same time, this we have this reverse flow and the spiral separation, large scale spiral separation on the wind surface. Okay, so this is the case with particular interest. We'll come back later. Okay, and here shows it's the result of this alpha angle 30 degree. Okay, this is a video. If not able to show the video, then I will use this mode, and you can see that, okay, this we have this strike vortex with vortex breakdown near this region. Okay, and okay, maybe you'll come back to this one, then you can. Okay, seems now it's doing well. Okay. Okay, so we this is for angle attack 30 degrees. So we have to clearly see the vortex breakdown of the string vortex. And let me. Okay, so the snapshot of the video. Okay, you can see this is straight vortex with the vortex breakdown, and yeah, it's difficult to identify the wind vortex from this video. So what I would like to say is that the visualization technique, yeah, able to show the different views, different aspect of the flow. However, would not be able to show all the aspect, okay, with each technique. So you need to use a different technique to see, to get more information about the from the different from different view angle, different way to get the information. Here shows again that okay, we show that at the alpha angle 30 degree, and yeah, in the water channel, okay, 1.5 10 to the 4, you can see by ink dot, you can see this very large region on this wind surface with indication of the flow outboard. Okay, and this is actually can be further indicated by wind tunnel auto film visualization at the 5.7 10 to the 4. Okay, in fact, in this case, you see that. Okay, actually, there's a secondary separation line associated with the wind vortex. Okay, and this is a large region where you have this outboard, okay, flow. And speaking of this straight vortex, yeah, if you have some, you have some idea from the previous video. Actually, it's a vortex breakdown around these junctions, okay, with the strike and the wind vortex. Okay, then speaking of this Reynolds number effect, okay, we are doing this wind tunnel experiment, oil film, okay, and ranging from 3.7 10 to the 4 to Reynolds number 1.2 10 to the 5. And yeah, you can see based on this visualization, what we can see in this at the alpha angle 10 degree, you see these two secondary separation line associated with the strike vortex, and the other one associated with the wind vortex. Okay, and meanwhile, from these images, we are able to get the distance, okay, from the origin. Okay, so this is the numbers, okay, given to indicate, okay, the location of this secondary separation line, okay, at this core location 0.9. So these are the indications. So we try to identify the locations of the characteristics of this strike vortex and the wind vortex. And also I should mention this arrow here indicate there's a discrete vortices associated with the wind vortex. Okay, this is actually associated with the shear layer developed from the leading edge, and due to the instability, yeah, these vortices develop, and yeah, let's copy from a paper, Gerhard, and now you also in our wind tunnel visualization, you also can identify this kind of discrete vortices. Okay. Okay, and yeah, this is again I mentioned this is the most interesting case. Okay, alpha angle 20 degree. Okay, and we have a range of the Reynolds number from 3.7 to 10 to the 4 to Reynolds number 1.2 10 to the 5. So you can see that. Okay, again you can identify this strike secondary separation line associated with the strike vortex, and the other separation line associated with the wind vortex, and the appearance, okay, actually changing, okay, with respect to Reynolds number. That's what we are particularly noted, and also indicated by this distance measured. Okay, speaking of the secondary separation lines of the two vortices. So compare the lowest Reynolds number and highest Reynolds number is very, very remarkable. Okay, speaking of the wind vortex, okay, at the high Reynolds number, this wind vortex secondary separation line is already moved more outward, outboard. Okay, so this is the case. I made here higher Reynolds number, higher the strength of the wind vortex relative to that of strike vortex. So we'll come back later. And at the Reynolds at the alpha angle 30 degree, again we check this a number of this visualization, obtain the different Reynolds number oil film visualization. In this case, we found Reynolds number effects not so significant as the strike and vortex interactions concerned. So you can see that basically, yeah, we see this secondary separation line associated with the wind vortex. At the same time, this arrow here indicate this location where, yeah, this vortex breakdown associate vortex breakdown of the strike vortex. Okay, so yeah, based on this oil film visualization, we are able to get this plot of this spin-wise location of secondary separation line, different angle attack with respect to Reynolds number and the chloride location, as I indicated in the previous photos. So particular attention is paid to this wind vortex separation line at the angle 20 degree. Okay, this is a significant, okay, move out the board, okay, as the Reynolds number increase, which indicate this is as a result of Reynolds number effect. Okay, it's a strongly interaction, okay, between the strike and the wind vortex. And this is really dependent on the Reynolds number. Okay, so I will go through quickly about this PIV result. Okay, and the PIV results made, okay, in the water channel at the 22 cross sections indicated here. Okay, it's covered the strike and the wind, a part of wind region. And at alpha angle 10 degree at this Reynolds number, we chosen 3 times 10 to the 4. Okay, on the left hand side, this photo indicate the total data. Okay, it's a 3D view of the total data. Okay, what we indicate here is a low speed. Okay, near the surface, which indicate at this angle attack, the vortex induced flow motion actually is not that strong. And on the left hand side, this is only the data points. Okay, with the velocity higher. Is normalized, which means it's a 5% higher than the free stream velocity. So the high velocity points is located upstream of the wind. So it's a kind of, okay, indication of not so strong of this high speed flow induced by this vortex. Okay, except this straight vortex is the point here. Okay, which indicate this associated with the straight vortex. Okay, then speaking of this 20 degree, again, this is the most interesting case. On the left-hand side, against the 3D view of all the data points, okay, we obtained. And you see here, there's a high-speed region, okay, indicated here is associated with the strike vortex. Yeah, the other one is associated, the high-speed region is associated with the wind vortex. This is what we found. Okay, and what we found is actually, yeah, it's associated with the stretching effect on the wind vortex. Okay, and speaking of this, yeah, we can refer to this visualization here. You can see this wind vortex and strike vortex strongly interact. In fact, you can also mention this is kind of very coherent around. Okay, very strong interactions, and this interaction actually depending on the Reynolds number. Okay, this is in wind tunnel 5.7 10 to the 4. And this one here, wind tunnel, water channel 1.5 10 to the 4, and the PRV is 3 times 10 to the 4. So it's kind of for you comparison. And here shows the PRV data points. Okay, again, this shows the points, the point for velocity higher than, okay, 20% of the free stream velocity. You can see that. Okay, so here we identify the strike vortex. Okay, vortex core here. Okay, high speed, and also we identify here is a region where I mentioned this strong interaction, long, and due to wind vortex, due to stretching effect. Okay, and again, this is shown due to this stretching effect. So let's come back to this spreading effect here. So what's happening is that the wind vortex coiling around this strike vortex, which induce this stretching, and this stretching actually accelerate the flow in the core region of the wind vortex. And this is what we found here, and this is very clear evidence of this effect. Come back to this 30-degree angle attack. Okay, and you can see on the left-hand side is the total data points, okay, of the PIV data, and it indicates this high-speed region associated with the straight vortex, and ended with the vortex breakdown is near the junction of the strike and the wind vortex, which is consistent with what we have observed in oil film visualization. And here I also indicate that put the dashed line here. This is indicate where the secondary separation line associated with the wind vortex, as you see from the oil film visualization. At the same time, we are from the PIV data, we see this high-speed data point. Okay, show a kind of boundary here. Okay, this is induced. This is the induced by the wind vortex. So we are able to kind of get a quantitative estimation of this wind vortex span-wise size. Okay, so here comes to the summary. Okay, so the result here we are presented. Okay, for 3 cases, low and the medium high angle attacks. Okay, it's the 3 distinct cases of interaction between the strike and the wind vortex. The low angle attack, the strike wind vortex, and the wind vortices are without significant interaction as the individual behave as individual vortices. Okay, yeah, largely speaking, and at the 20-degree angle attack represent a case strongly interaction, okay, between the wind and strike vortex, and which is very sensitive to Reynolds number. And at the angle attack 30-degree, okay, the breakdown of the strike vortex took place near the junction of the strike of wind, and the interaction, yeah, appears not as significant as the angle attack 20-degree. So finally, I'd like to share this photo with you. Okay, this photo I took just a few days ago. It's indicate that the regulation here due to COVID-19, yeah, now we relax a little bit. People are able to have exercise, open fields. However, everyone need to wear a face mask. Okay, so my best wishes to everyone, okay, during this period of time, COVID period of time, healthy and happy. Thank you very much.
Thank you very much, Prof. Miao, for the presentation. It's very interesting. I now open the session for question and answers. Should anybody like to ask questions? I'm pretty sure the talk have triggered some sort of thinking. Yes, please. Thank you. Any questions? Dr. Shabuddin?
Not easy to ask. It's very good results and vortex interactions between the primary and the new one. Congratulations to NCKU team.
Okay.
We will try to compare that with the wind tunnel here.
Yes, yes. I believe this, I'd like to point out Reynolds number effect, yeah, can be very important in a number of cases. Okay, yeah, it's a very complicated and challenging issue for study. Yeah.
Prof Miao, can I share something with you? Okay.
Yes, thank you, please. Yes.
Prof, at the moment, I have a PhD students looking on this delta wing, which is based on the Maldicon wing, actually. So he's already halfway on the PhD, and he got some, promising results on the basic aerodynamics of the CL, CD, and CM of the aircraft. And then, yeah, we also encounter very interesting phenomena at 20 degrees of angle of attack. So we also looking into the uncertainties on that experiment, but purely based on the force and moment measurement. But yeah, I think I will like to convey, maybe we can collaborate something that, because we look at your flow visualization is very, very good. So in the future, I think maybe we can talk after this that that model can be tested in your facility and to correlate the forces, aerodynamic forces and moment that we have to the ocean, because
Oh, Dr. Prof. Suhaimi's link is unstable.
impressed.
Prof. Suhaimi, your link is unstable. Can you repeat the question again?
Into the Meow, is it? Can you hear me, everyone, now?
Oh, yes, now, yes. Okay. Can you repeat the last minute?
Yeah, we were happy to collaborate with you because we are impressed with your flow visualization, so we can correlate the flow vis and the wind tunnel force and moments measurement.
Thank you. My pleasure. Okay, Professor Swami. Okay, certainly my pleasure. Yeah, looking for the future for the collaborations. Okay, yeah. Thank you.
Are there any other questions that would like to present to Prof. Miao?
Assalamualaikum, Mr. Chairman.
Yeah.
Maybe I have one question. Just want to ask about. Hi, Professor Miao. How are you?
Yes, yes, yes. Yeah.
Okay.
Professor
Okay.
Azumi,
I just want to ask. Many of the delta wing and also this research is most focused to the vortex flow, all that. What are the significance of this when we study related to the aerodynamic point of view? Is there any significance? Because many of the researchers just study about the flow. Is there any effect that related totally to the performance of the aircraft itself? Yeah, I just want. Maybe I'm not really.
Yeah, just based on what I know and my understanding about your question. So, vortex flow certainly is very important for this kind of configuration for lift and the aerodynamics. And speaking of this Reynolds number effect, yeah, what we found is that, okay, yeah, probably not only this lift drag, okay, is could very significantly affect this pitching moment, okay, and so on. So yeah, to understand vortex and vortex interaction, okay, helps to get the better, okay, data, okay, accuracy of the data, or to get the better understanding of physics of the configuration. For instance, Professor Swami mentioned about the multicon or the sacron. Okay, all this kind of configurations, okay, quite complicated with the vortex, with the effect to due to the Reynolds number.
Maybe I can chip in a little bit, yeah. From
Yes, Prof.
yeah, because normally we use potential lift to lift the aircraft, yeah. But for the high angle of attack, we hope that we're gonna get vortex lift from the aircraft. But however, with the delta wing, as the lift increases, they give, I mean, unsteadiness to the pitching moment. So then the stability of the aircraft getting worse actually. So we actually trying to understand the flow vis, so we can mitigate the unsteadiness. Hopefully we can get a better stability in terms of pitching moment, and maybe later in the in lateral motion as well. So that's actually the direct impact on the performance stability of the delta wing to get the vortex lift from high angle of attack. I think, yeah, that's Prof. Miao. Yeah.
Thank you, thank you, thank you very much for the comments. Yes.
Thank you very much, Prof. Shaimi. Right.
Yeah.
I think,
Uh,
are there any other questions? Yes,
I know.
Mahir.
Yeah. Hello, Professor Miao.
yes,
My name is Muhammad Khair. I'll be one of the speaker later on. But
yes.
anyway, it's interesting. Can you elaborate a little bit on the use of PIV in your system measurement? Because PIV is what I understand is very complex, very system because of you interpret the image and so on. How complicated you want to use and interpret based on the PIV results of measurement. Thank you.
Okay, the system we have right now actually is developed in our lab. Okay, the function is not that high level. Okay, so we have just a 2D cross-section measurement. Okay, 2D measurement, and in the water channel, which means okay, we are able to use lower frame rate. Okay, so that's easier for image processing. Okay, and of course, there's number of issues need to be developed to be clarified. Okay, a student need to try, for instance, exposure time and the time between two frames and so on. Yeah, and how to manage these softwares. Yeah, that's take a little bit of time. But all this, I just leave student to let student do this. Okay, yeah.
Right. Thank you very much, Prof. Miao, for the explanation and the responses to the questions. We move on to the next speaker for today's seminar. Prof. Miao, can you unshare?
Okay, so I needed to just a minute.
Okay.
Thank you, Prof.
Our
Miao.
next speaker is Prof. S. Tanya Gayarasu from Anna University, India. He's an illustrious alumnus of IIT Madras and Madras Institute of Technology, Chennai. He carried out his research in the field of high-speed jet controls and received his PhD from Anna University, India. Prof. Tanya is also an expert in the field of high-speed jet controls and computational heat transfer. He has published more than 100 papers in international journals, and he's going to publish a book, Computational Fluid Dynamics and Heat Transfer. And currently, he is the head of the Department of Aerospace Engineering, Madras Institute of Technology, Anna University, Chennai, India. So can I invite Prof. Tanya to give his presentation? Prof. Tanya, are you there? We cannot hear you, Prof. Tanya. By the way, Prof. Miao, can you unshare your presentation? Okay, yeah. Okay, Prof. Tanya, we still cannot hear you. We cannot hear you, Prof.
Let me call him.
I think maybe it's something to do with your audio settings.
Yeah, 1 minute. I'm just.
Oh, okay, we can hear you now.
Oh, is it? Okay, very good.
Okay.
Yeah. Are you able to see my presentation?
Can you go into the presentation mode?
Yes. Yeah, sure, definitely. Yeah.
Oh, okay, now get.
Yeah, can you hear me now?
That's
Thank
good
you.
now.
Okay.
We can hear you clearly. Yeah.
Very good morning to all the participants of this ISAE 2021. It gives me a great pleasure to participate in this workshop, international workshop from India. So, of course, as I used to say, Malaysia is my. I used to visit Malaysia many times, the universities. UPM and ISAE also I've attended. Really, again, I'm having some interaction with you all people. It gives me great pleasure. So my presentation is going to be on the shape transition effect of the isolator that is used in the scramjet engines. It is supersonic ramjet engines. And my presentation consists of the two parts. One is a numerical simulation and the experiments we have carried out on the shape transition, the effect to predict the static pressure and the shock train length of the isolator. So you may be thinking that the isolator, which is an integral part of the scramjet engine, or the integral part of the inlet, maybe the external as well as internal compression inlets are there in the scramjet engine. But the role of the isolator is very important in even that it decides the entire performance of the engine, scramjet engine performance. So it is the need of the hour to study the characteristics of the isolator with various shape transition mode. And the objective of this research is to, as I already told you, to predict the characteristics of isolator when there is a shape which is changing, maybe from circular to square or square to circular or square to elliptical transitions. And also to visualize the shock train of the isolator, in which is the facilities available in our laboratory. And you know that the isolator is an important component of the supersonic combustion ramjet engine, as I already told you. This is the ramjet engine, and which consists of the components like C4 body, which acts as an external compression inlet, and we have another. After that, we have internal compression inlet, then isolator, combustion chamber, and nozzle. Of course, we have a half body. So what is now the isolator is in place between the combustion chamber and the inlet. Then what is the need of the isolator? Let me first discuss on this. I think isolator is somebody, it would be a new word they may be hearing. So only I'd like to give some introduction on the isolator, and then we go to the work we have carried out on the isolator. Okay, so the isolator is a component, as I already told you, is placed between the combustion chamber and the inlet, that is especially the internal combustion inlet. The reason is that it separates, that it isolates combustion chamber and the inlet. The reason is that when we inject the fuel into the combustion chamber of a scramjet engine, the fuel would be atomized first, and then it would be vaporized and it gets mixed with the air stream, which is moving at a supersonic speed. So a lot of complications are there in the supersonic combustion. Not only supersonic combustion, before the process of combustion, we have a lot of complications like atomization and vaporization, the mixing, because the speed of the air stream in the scramjet engine is highly supersonic, for about 1.5 to 2. Nowadays, I think they can reach even 2 in the combustion chamber of the scramjet engine. When the fuel is injected, the fuel would be split into form of droplets, and the droplets also would be having the same energy as compared to incompatible with the air stream. So that means obviously that is the requirement. And when the fuel is injected in the form of droplets into the combustion chamber, and when the fluid, the supersonic air is moving in the combustion chamber, and when a solid or the droplet interacts with the supersonic stream, obviously there is a presence of the shock, the formation of shocks will be there. So that means this is a major problem we would be facing as far as this supersonic combustion is concerned. So these droplets, it is not a single droplet. Multiple droplets are injected, obviously, continuously into the scramjet engine, and as it is a continuous combustion. We all know that, and these droplets acts as an obstruction into the supersonic air stream, and that would form the interaction of the droplet and the supersonic air stream in the combustion chamber would form a kind of compression waves, and these compression waves would coalesce periodically, and that would send a static pressure rise in the upstream direction of the engine. Upstream direction means towards the inlet. Here we have two parts here. So downstream direction of the combustion chamber and upstream direction of the combustion chamber. Upstream direction means inlet. Downstream direction means in the nozzle. We have nozzle. So we have in the downstream direction of the combustion chamber, we have nozzle and we have favorable pressure gradient, and there is no issue about that. But in the upstream direction, we have adverse pressure gradient because we have already we have an inlet, and that gives air static pressure when the air enters into the inlet because of the shock train formation and all. So this the upstream direction, now there will be a favorable pressure gradient that would exist because of the formation of shocks in the combustion chamber. Favorable pressure gradient means the pressure, the downstream direction, that is in the combustion chamber, we have the static pressure increase would be there. So instead of moving in the downstream direction, the flow would it would start moving towards the upstream direction. So that means there is a change in the back pressure at the exit of the inlet, assuming that there is no isolator. So when there is a change in the back pressure would even make the inlet to unstart. That means the entire shocks would be pushed out of the inlet, and the inlet would become unstart. You know, when the inlet becomes unstart, and if it is working on under unstarted condition, that will definitely affect the performance of the engine, because the required mass flow rate may not be there, and so on. So only we keep a component which is a simple duct placed between the combustion chamber and the inlet. So the disturbance carried from the combustion chamber is completely diluted by the isolator, which is a simple duct. Okay, so the disturbance is diluted in the isolator, so the isolator prevents the inlet in going for unstarted condition. So only we have this the isolator. And let us just briefly, I'll just quickly go through the isolator. As I already told you, it is a simple duct. Okay, so as you can see from this diagram, if the isolators, suppose if we have a simple duct and supersonic flow exists in the simple duct, and obviously there is no constant, there is no area change. Obviously, there won't be any significant change in the properties because the area is constant, even though the flow is supersonic in a simple duct. But if the Mach number, supersonic Mach number increases, and that will and supersonic Mach number increases, the boundary layer growth in the duct, simple constant area duct itself would be subjected to maybe the thickness of the boundary layer would change. And if the thickness of the boundary layer changes, this would have an effect on the flow in the constant area duct. So this change in the flow properties, obviously, as we might have studied in a shock wave boundary layer interactions and all, the growth of boundary layer definitely affects the core flow. That means the cross section of the flow itself would change. So that will also pose some kind of change in the properties in the duct. Okay, so this boundary layer growth and the supersonic flow that moves into the constant area tube would try to interact with each other, and that would finally try to form a kind of shock waves. So the interaction of the supersonic boundary layer with the supersonic flow would form a shock pattern after a particular supersonic Mach number. So that would, as I already told you, this boundary layer formation would obviously form a series of shocks. As you know that there is an area change, core region area changes there because of the boundary layer growth, and this boundary layer growth would result in formation of series of shocks. This series of shocks would try to travel into the core region and then hits the other top surface and the bottom surface respectively, and that would get reflected as expansion fan and then again compression waves. So these reflection of a compression wave and expansion of fans would form a kind of shock train in the boundary layer, shock train in the isolator. That means isolator, now what is isolator? It is a simple duct which contains a shock train. So if you don't have a shock train in the isolator, obviously the disturbance, as I already told you, generated in the combustion chamber would not get diluted, because there is no, it's a simple duct. Whatever the condition is there in the inlet, the same condition would be existing all along the simple duct if there is no shock train. So the prerequisite of the isolator is that we must have a shock train, and of course what would be the length of the shock train, and what would be if we have a longer shock train, and that would definitely increase the drag, and also it would also increase the heat transfer. Okay, heat transfer effect to the walls and all. The material selection also would become a challenge. So we should optimize the shock train, because the shock train would is the one which prevents or dilutes the disturbance that is coming out from the combustion chamber. in reaching the inlet. Okay, so that inlet is protected in going for unstarted condition. So this is what about the shock train. And of course, there are various regions are there in the isolator. As I already told you, this is the shock train, which is the series of shocks, and we have shock cells also. We have and after the shock train, we have the mixing regions. So we have mixing regions and the shock train region, and this the combination of this mixing region and the shock train region is called pseudo shock length. And of course, this is what I've told you now. The shock train plus the mixing region is nothing but the pseudo shock, which we are going to now discuss in detail. So this is the shock train formation in the isolator, and you can see that obviously at the start entrance or the leading edge of the isolator, we have a steep increase in the static pressure that would try to that is the indication of the normal shock and the strong normal shocks, because the steep in the rise in the static pressure is observed in the isolator, and this try to interact with the boundary layer and gets reflected. And then it forms the series of shock train. And as I already told you, this the fluctuation in the static pressure is the presence of the shock train, and the presence of the shock train in the isolator. And after that, after the shock train, we have the mixing region. So this is what about the isolator. And of course, this shows that we have a cylindrical duct and a planar duct. So it is clear that the shock train obviously would be different with respect to the geometry of the isolator we use. So only we have decided to go for different geometries, and we have decided to predict the performance of the isolator with various transition. And this is an example of the shadow graph picture we have obtained in our laboratory for the square duct at different NPRs, that is NPR 4, 5, 6, and 7. And you can see that though it is a simple picture, you can see, but lot of information we can get from this shadow graph picture for various NPRs and all. You can see one observation is that if you compare NPR nozzle pressure ratio, NPR means the nozzle the pressure ratio, and which is if you take NPR 4 and 7, we can see the weak normal weak reflections are taking place inside the duct. We are not able to see, we can see some waves, but we are not able to see the shock cells and the interaction, and even shock train we are not able to see. But here at NPR nozzle pressure ratio 7, the chamber pressure is very high, and the formation of the shocks are very much clear here, and these shocks gets reflected from each it looks like that the shocks are getting reflected from the solid surface, but if you enlarge the figure and if you do some analysis, it can be understood that the reflections should be taking place not from the solid surface, but it is from the boundary layer. Because the boundary layer growth, we know the shock boundary layer interaction. The boundary layer consists of both subsonic and supersonic flow, and the shock would penetrate into the boundary layer as long as the flow is supersonic, and then it would get reflected, and the shock also would be bent inside the boundary layer. And so there are two observations we can make from this. As the NPR increases, the strength of the shock also increases. So as you can see from this, slowly the strength of the shock is clear. The dent is seen at a higher NPR and all. This is a shadow graph picture we have obtained. So I just wanted to say what is shock isolator and what is shock train. So for that purpose only, just display this figure. Of course, the Waltrop and the Billing correlation is a very famous correlation which predicts the pseudo shock lengths and all. And of course, we have used this formula for validating our results. And of course, as I already told you, my presentation consists of two parts. One is a numerical simulation, and along with my research scholars, we have carried out. And of course, some shadowgraph picture we have obtained the soft train of the isolator for various configurations. Okay. The unit the Reynolds number is now 12.4 10 to the power of -6 per meter. The unit Reynolds number. I've used the square and the square to circular configuration of the duct, square duct and the square to circular duct. There are two configurations I've used in this numerical simulation, and we have obtained the shock train and static pressure variation, Mach number variations in the Mach number variations. So from this, it is understood that the length of the we have maintained the length of the shock train is 90 mm, and the Mach number that at which the flow enters into the duct is the exit is 1.6, that's supersonic at NPR 7. So you can see from this that we can see Mach disk formation is clearly visible here, and the first cell. And after that, the strength of the Mach disk is completely slightly getting weaker, and finally at the end of the duct, it is almost we are not able to see the shock train and correspondingly we can see the static pressure variation. The static pressure starts increasing. We all know that if there is a shock shell sense of the shock, the static pressure variation increases. The static pressure increases taking place. So as I already told you, not only the isolator performance is not only to prevent the inlet, not only to prevent the inlet from unstarting condition, but also it would acts as an inlet. It acts as an inlet because we know that there is a presence of shock train. This shock train would definitely increase the static pressure, and higher static pressure of the air stream would get into the combustion chamber. Okay, so in this the Mach contour. This slide shows the Mach contour, and of course we can see that the Mach number. We can see here the series of shock cells are very significantly. We could see the Mach number also decreases as you go from here. You can see from here the higher Mach number is there, approximately Mach 2, and that's getting reduced because of this for the square duct. It gets reduced. The Mach number also gets reduced. And we could see the shock cells here. 1, 2, 3, 4, 5, 6, 7. Around 7 shock cells are there. And initially, the first cell has got a higher shock strength. And of course, the Mach disk formation also is visible here in the square duct. Of course, this is the density contour of the square duct with the shock train of the same length. L is equal to 90 mm at NPR 7. And when we change the length of the duct and keeping the supersonic flow Mach number of 1.6, the length of the duct changes. The significant changes observed in this because we have kept the Mach number the same because it is supersonic Mach number 1.6. And even though if you change the length of the Mach number, if you change the length of the duct, the shock train after a certain length, the shock train completely disappears, and we have only the mixing region. Okay, so we need not have the length of the duct as we like. So we should predict the presence of the shock train, the length of the shock train first, And based on that, we can go for deciding the length of the isolator. Okay, so for this to get some kind of inference, we can use this study so that we can optimize both length of the isolator and the pseudo shock length. So the observation we make here is that if you keep on increasing the length for the same supersonic airstream, okay, inlet Mach number is 1.6. Okay, obviously the length of the shock train is different here. You can see the length of the shock train also is different, and of course after certain distance, the shock train is not at all seen. You can see so here. Off of the portion we can see the shock cells and the shock train, and maybe after L/2, I think you are not able to see any kind of the shock trains and all, and there you have completely the mixing regions. If you have the same as the supersonic plant, if you change the length of the isolator, that would increase the mixing region, not the shock train length. So that is the observation we made. So the mixing region would increase if we keep on increasing so that would become ineffective because as long as you have a shock train, that would definitely do favor for us because that would try to dilute the disturbance that emanates from the combustion chamber. If you have simply the mixing region, and of course that is not completely okay. Our objective to have a more mixing region. We would like to have a shock train, maybe the stronger shock train that would easily prevent the disturbance emanating from the combustion chamber. So if you have a stronger shock train, the length of the isolator would be shorter. Of course, that would have some advantage of having reduced drag and weight and other things. So we have to have some kind of this one compromise in this. Of course, for this is for various aspect ratio means for varying the length. I've just consolidated in one this one. And so NPR 7. Yeah. So for various Mach numbers. Okay, for this is the Mach number, various Mach numbers, and at NPR, this is the distribution of the shock train along the isolator, shock train, and you can see for various NPR, for various Mach number, there is the location of the Mach disk also changes. You can see from this diagram, Mach number 1.6, 1.8, and 2. The location of the Mach disk changes. It gets postponed. Maybe after some distance, the presence of the Mach disk is observed. The first Mach disk is observed, and also the length of the shock train also is different. You can see this observation. Say for a higher Mach number, the shock train length increases. The higher Mach number, the shock train length increases. You can see from here. Maybe from 0.7 to 1.68. There is the shock train is lengthier for higher Mach number. For the constant area having the same length, L is equal to 150 mm. Okay, so like this for different NPR. So in the previous slide, we have mentioned that as the Mach number increases, the length of the shock train also increases. It's obvious, and for different NPRs, as I already shown you one shadowgraph picture, as the NPR increases, the shock train also increases. Shock train length also increases, and also the shock strength also increases as the NPR shock strength. You can see from here. So at NPR 6, and this is our NPR 7. and the strength of the shock is a function of NPR, and the length of the shock train is also dictated by the geometry and all. And of course, the square to circular duct, so far we have seen the square duct, and we just we'll just go through this results of square and the square to circular. This is the contour of static pressure contour of the square and the square to circular configuration. So you can see from this diagram, the static pressure variation is observed in the square as well as square to circular configurations. You can see the shock shells. Also, there is a difference in shock shells pattern. There is a difference in shock shell pattern in square as well as in the square to circular. Let's see what is the cause of this difference in maybe even in the upcoming slides. And this is the Mach number contour of the square duct and the square to circular duct. Of course, we could observe in both the cases, we could observe the shock train, and the mixing region also is different, and the shock train length is also different, and the mixing length also is different. That means the pseudo shock length is nothing but the combination of the shock train length and the mixing region is completely different. It is dictated by the geometry as well as the Mach number. So we have measured, and also we have got the results from the simulation along the length of the wall pressure, wall static pressure, along the length of the isolator, and wall static pressure we have measured. As we could see, there are two regions we could observe. We are able to capture from here. There is a fluctuation in the static pressure. There are two plots we could see from here. One is for square and one other is for square to circular. And there is a difference in wall static pressure variation. And as you can see from this, the square to circular is represented by the dotted line, and the square is represented by the solid line. So there is a presence of the fluctuation that indicates the presence of the shock train. And of course, after certain length, the shock train vanishes, and the mixing region is taking place where there is no the shock train. So that means the pseudo shock length also is different with respect to the configuration. So that would definitely, these studies would definitely help in designing the isolator. So here in this mixing region, we have to try to reduce the mixing region. So for that, at what length the shock train vanishes is very, very important. At the what length the shock train vanishes. You can see from this, the fluctuation is observed for the square to circle combination for even up to 80% of the length of the isolator. You can see from here, the dotted line represents the square to circular wall static pressure along the isolator, and that the fluctuation exists for longer distance. So the shock train is lengthier lengthier for the square to circular combination, and the shock train. I'm talking about shock train, not pseudo shock length. Okay. So the fluctuation, I'm talking about only the static pressure fluctuation. And for the square duct, the fluctuation is vanishing after approximately 75% of the length of the isolator. So I think we all know that when there is a square duct, it has got 4 corners, and these corners, obviously there is a lot of difference between flow in a circular duct and flow in a square duct because of the corners effect. So these corners obviously would form the vertices of elliptical shape. You will have a various size of vertices, significant variation in the formation of in the size of the vertices. But here the corner vertices would be responsible for making the shock train shorter as compared to the square to circle configuration. So if it is understood that if you have square or non-circular configuration of the isolator, we can have a shorter short train. And if you have a shorter short train, if you have a circular configuration, I think we will have a longer mixing region. So longer the mixing region. So that is the observation. This static pressure distribution along the isolator wall is center line. So this is the center line variation. Center line variation of the last plot we have seen the wall pressure variation, and this is the center line variation where the slide the fluctuation is very mild fluctuation is because both the stocks would try to get it would interact and in result the fluctuation is.
Can you please wrap up the presentation?
Yeah, sure, definitely. Yeah, so I'll quickly go through this. These are the wall stress contours of the square and the square to circle, and we have already validated the numerical as well as the result which is obtained from the literature, and it is in line with the whatever that simulation we have carried out is validated the already existing literature and all. And of course, this is the pseudo shock length. As I already told you, pseudo shock length is different with respect to the combination. That means the geometry of the isolator dictates the pseudo shock length. Not only pseudo shock length, the shock train and also the mixed region. So which one you would like? These are the comparisons of pseudo shock length and the shock train. You can see the shock train length and the pseudo shock length and all. Okay, of course, the drags also we have numerically calculated drag. If the length of the shock train is more, drag also obviously it would be more. And of course, these are all the similar results presented in various forms. Okay, so we also did some simulation with the elliptic configuration. This one we have seen square to circle, and now square to elliptic configuration also we have seen. And in this case also, we have observed a lot of change when there is a change in the configuration. So this is the comparison between square to circle, and square to elliptical configurations. Of course, as I already told you, the square and elliptic square to ellipse would have a relatively shorter shock train, and as compared to a square to a circle, and obviously corresponding change in the mixing region. This is the wall static pressure, and of course we could see the shock train easily. And experimental results also we have extracted from our experiments for various configurations, square to circle and square to ellipse and the square. And we could see the fluctuations, and that shows that the presence of shock train and the various length of the shock train also is different. Static pressure variation also is different with respect to the configurations and all. So those things are also observed in our laboratory. These are, as I already shown you, this shadow graph picture of various isolators, and which contains the shock train. And the conclusion is that obviously the shock train length is dictated by not only the Mach number, but also the shape of the isolator. And correspondingly, the static pressure variation is also observed. That would be different from for different configurations and all. And we have also validated the numerical simulation results, and also we have got some idea about the shock train by having a visualization in our laboratory of isolators. So these are the references, and we have also published a few papers in journals, in reputed journals and all on this isolator. The work is not completed. We are on the process of finding out many things in the isolator performance. So with this, I think I thank Professor Sabudin for having given me an opportunity to interact with you all and for having given me a chance to present on this again. Thank you very much. You have any questions?
Thank you very much, Prof. Tani, for the presentation.
Yeah.
And I think we can open to the floor to ask questions and to discuss the topic
sure.
of the isolator.
Yeah,
Yes, please. Hanafi?
Hanafi.
Yes, thank you, Prof. Tani, for the nice presentation of your work. That's good because same our research almost the same. I used to study the detonation engine. So I want to ask three things. In IIT, do you have this shock tube in your lab? That's number one. Number two, would you think that if you are using a square and rectangular, will it be much better than square to square? And then my number three, what do you think if you try to reduce the area of the insulator? Thank you.
Yeah, actually, the first question is that whether I have a shock tube in my laboratory. Shock tube, yes, of course, we have an experiment on a shock tube in our laboratory. That is, you mean to say shock tube or isolator? Isolator, obviously, we have, but the shock tube purpose is different. That is for combustion character, prediction of the combustion characteristics. You are asking shock tube or isolator?
Shock tube. You have shock tube as well? Yep.
Yeah, we have shock tube experiments. Our students are working on this shock tube experiments, and they find out at various rupturing of the diaphragm. They are finding out what would be the pressure at which the diaphragm ruptures at various thickness of the diaphragm. So, and all those things they are seeing. So, yes, we have on shock tube, a small shock tube in our laboratory. And the next question is?
Next question related to the shape of rectangular as compared to square. What do you think?
Yeah, rectangle and square. It's a very nice question. Since you are also working on this isolator, it is very easy to compare this square and the rectangular isolator. The reason is that if you use this rectangular isolator and you have aspect ratio, that would make the shock train or the flow still complicated, because if you have a rectangle, you have a major axis and the minor axis, and that would also try to alter the flow, because there is one phenomena that would try to take place because of the interaction of the core with the boundary layer, and the complicated flow would definitely become complicated because of the phenomena that is called on axis-switching phenomena would also take place. Of course, not like what we could see in the open jet facility, but even inside, there will be a slight, the flow would become complicated, and so that would also assist the what we can say the shock train, the shock train formation. But the square is stronger because the aspect ratio is 1. All sides are equal. The vortices generated from the corners would easily travel all the cross sections, and that would be more effective as compared to the rectangular one. And it would make the isolator length shorter. And as you said, as we already discussed, the weight of that would also reduce the weight and all. But in the case of rectangular one, what I feel is that we will have a slightly longer shock train, and that would also make the isolator to have a lengthier one. So I hope. Are you clear?
Yeah. What about the last question? If you try to reduce the area of the insulator, have you tried this?
Yes. So your question is that if you have a shorter length of the isolator, what will be the effect?
No, reduce the area.
Reduce the area of the cross section. Yeah, but that is nothing but the aspect ratio. Aspect ratio changes. It would definitely have some influence, significant influence on the short train length as well as the mixing region. And if you say that, okay, what will happen if you increase the area and area of the cross section willing to change? Obviously, if the area is reduced, the shock strength would definitely increase, because the reflection, it would the shock that emanates from the boundary layer formation, okay, that would coalesce into a single shock and then gets reflected from the outer edge of the opposite edge of the boundary layer. If the area is larger, okay, the arctic cross section, the strength of the shock also would vary relatively as compared to the shorter length. And the interaction, that means the viscous interaction, weak and strong viscous interaction, as we might have studied, also would differ with respect to the area change, because the core cross section area would definitely would change with respect to the boundary layer growth, because you know the boundary layer growth is not only a function of the Reynolds number here, but also it's a function of Mach number. Not only the function of Mach number, the square of the Mach number. So these obviously would influence this short train.
Okay, thank you very much, Prof. Dani, for the explanation.
Yeah.
Unfortunately, we do not have time for more questions.
Yeah.
So I would like to wrap up this first session, first keynote session, by thanking all the distinguished guests who have presented today, Prof. Josh Barakos, Prof. Anton Nadibroto, Prof. Junji Miao, and Prof. S. Tania Gaya Rasu, who have enlightened us a lot about the developments in the field and related areas. So we'd like to again thank everybody for your presentation, and we hope that what have been presented can be benefited by everybody. Okay, thank you very much.
Thank you.
Okay, we will now move on to the second block of sessions with keynote session number 2. Prof. Tanya, can you please unshare your presentation?
Yeah, definitely. I'm trying now.
For keynote session number 2, we have 5 speakers who are the former heads of lab of Aerolab. Okay. Beginning with Engineer Muhammad Khair bin Muhammad, who was our first head of Aerolab, followed by Professor Dr. Nazri Mohd Jaafar, and then Professor Dr. Engineer Suhaimi bin Mansur, Professor Dr. Engineer Wan Khairuddin Wan Ali, and Engineer Dr. Shabuddin bin Wan. For this session, we will have a 20-minute presentation, maybe about 15 minutes of presentation and 5 minutes of question and answers for every presenter. So the first presenter today is Engineer Muhammad Khair Muhammad, who received his Bachelor of Science degree in Aeronautical Engineering from Wichita State University and a Master of Business Administration from University Technology Mara. He is the first head of Aerolab, who was responsible for the planning, design, and construction of Aerolab wind tunnel from 1994 to 2003. He later left UTM and involved in other project works related to telecommunication infrastructures, fabrication of platforms and offshore structures, and international procurement. Currently, Engineer Muhammad Khair is also actively serving learned societies and engineering regulatory bodies, such as being the Vice President of the Institution of Engineers Malaysia, IEM, and also on the Board of Engineers Malaysia, and on the board of quality. He's also on the board of Quantity Surveyors Malaysia. He is currently also the Secretary General of ASEAN Federation of Engineering Organization, AFEO. So without further ado, I would like to invite Engineer Muhammad Khair Muhammad to give his presentation. 15 minutes. Thank you very much. Can you go on presentation mode, Engineer Muhammad Khair?
Hello, can you hear me now?
Very clear.
Okay, give me 1 minute to was started before, but can you see my presentation now?
Yep, it's up now.
Okay. Thank you very much, Prof. Aino Lutfi, for a kind introduction. My apology for a slight technical error here. Bismillahirrahmanirrahim. Assalamualaikum dan salam sejahtera, and good morning and greetings to all colleagues here, especially to the management and the official of the faculty. I saw the Deputy Vice Chancellor was there, and then the Dean, the head of the school program, as well as most importantly to the chair of the organizing committee, Dr. Shabuddin, all keynote speakers, distinguished guests, old friends, other friends and colleagues, and all participants. Assalamualaikum and salam sejahtera. Okay, first of all, thank you very much to be invited today. UTM LST or Aerolab. UTM LST stand for Low Speed Wind Tunnel, is always something that I'm particularly proud of as a person, as well as a practicing engineer. And I consider this is one of the most significant involvement and contribution toward my professional career. So when Dr. Shabuddin invited me to be in, I'm very pleased and honored to be back here to share some of the experience before on the wind tunnel work, and in the occasion of the 20 years of operation of the wind tunnel lab. So very unfortunate that we unable to meet face to face, but it's good to see how many friends, colleagues of my former colleagues here at UTM are here today virtually. My first slide, just not so much of important, just to give a bit of background of my talk today. The reason is because I was asked to share a bit of experience during the planning and the implementation of this project of having a new wind tunnel. So I was the project leader from 1994 to 2003. That is a total of 9 years leading the lab during that time without wind tunnel first. Okay, my only wind tunnel experience during that time is just doing a bit of wind tunnel testing at Wichita State University as part of my project at Wichita State, and that is doing the aerodynamic testing on the prop delta wing, pressure distribution on delta wing, as what being shown by the Professor Miao just now. So I'm very excited. For over more than 35 years now, a lot of development, especially on PIV on the delta wings. Later, I spent some time as a researcher in the transonic flexible wall wind tunnel, adaptive wall wind tunnel testing. And then 1994, I was appointed as the head of the Aero Lab. And in this project, I have involved in all stages of project, especially during the preliminary planning, as well as involvement until it's become operational. And also based on this project, also I got opportunity to be attached and working visit to various wind tunnel facility, including the first presenter, Professor Anton, was training just now on the LAGG Indonesia, NRC, National Research Council wind tunnel in Canada, the France, spent there 2 months, of ILOS Engineering Canada, as well as some vendor of the Microcraft USA. They are doing the platform. I show this picture. This is picture of 2001 when the first tunnel, when the building ready. This is the head of the lab office, and this is on the level 2, upper level. There are 2 levels, ground level and first floor. And if you see on the right hand side, there is behind me just the glass partition there, so that I will be able to see what's going on the test section area. So that is a advantage during that time, because I also involved with the design of the building. You design something that is useful for you, and also the building, the office also equipped with CCTV where you can do the testing or you can watch the testing. Okay, my title of presentation is the from dream to reality. I will explain later on why I say it's a dream, because when we started the wind tunnel project, this is part of the aeronautical engineering program at UTM since 1980s. So during that time in Malaysia, it's only UTM, as well as later on a few other university, University Putra, and if I'm not mistaken, also USM have some engineering related to the aeronautical and aerospace. But on the aircraft engineering side, is UTM is the pioneer, or the only university. Even that is also more related to mechanical engineering field, but purely aeronautical. So that program was a joint program between the UTM and the TUDM. TUDM means Royal Malaysian Air Force. Basically, their engineering officer upgrade their academic qualification to engineering diploma as well as a degree officer. During that time, the first wind tunnel that I encountered at UTM is this wind tunnel on the, we call it the blower wind tunnel. The blower wind tunnel is a plane. I think they got it, UTM got it during the loan from the World Bank, if I'm not mistaken, or the Islamic Development Bank actually. So it's a small wind tunnel, and that's good enough for the work for teaching, laboratory teaching of the aerodynamics. I remember during that time, Professor Suhaimi, when I first joined, they were talking about Professor Suhaimi doing the aerodynamic testing of golf ball in this yellow wind tunnel. We call it a blower wind tunnel. You can see blower wind tunnel straightforward without the diffuser in this case. Okay, it's a blower type. Later, when we moved to Johor, there's another wind tunnel. Actually, they call it sometimes it's big elephant because of considered huge during that time, or the blue wind tunnel because of it. This is quite interesting wind tunnel because this wind tunnel, maybe correct me if I'm wrong, wind tunnel we got it from the Singapore Poly or Nanyang Polytechnic from Singapore, if I'm not mistaken, from one of those, I can't remember. Yeah, okay. Thank you very much. So when we got it, you can see it has now, it have a two working section or dual working section, but in actual, the front section actually is being modified when the Aerolab, we bring back to Aerolab. So it's only small section here. So during that time, the late Professor Abbas and the team during that time extended to make it as for wind engineering sort of testing, which is not good, but it's just good enough for the instruction and basic laboratory teaching. So this is now I saw it's a bit longer now. I'm sure they have done a second modification on this one. So basically, the wind tunnels or things during that time is to support the education and the R&D, which is the laboratory teaching and the test activities in aero-related area, and to provide the testing and consultancy services to a related area. So these are basically the main equipment that we have during that time. Okay. So when I was given the job as a head of Aerolab, the first thing that we want to plan is just to have a proper wind tunnel for reasonable size, with reasonable quality for operation purpose. And in the late of 1980s, we already put the preliminary lab requirement of what we want to do. So during that time, it was proposed under the 6th Malaysian Plan, but unfortunately, we were not successful because the budget will be coming from the Ministry of Education. It's the government's budget because of we are under the Ministry of Education. So as early as late 80s, before I came in also, there's already some preliminary plan on what to do and so on. This is very interesting. So when I came in 1994, during that time, we sort of have to start all over again, fresh, because of a lot of people during that time, the early part is not there, and then some went for the further study and so on. But in 1994, when I was appointed by Professor Afifi that time during the dean, one of the big tasks is just to plan and set up of this new aeronautical lab with the major facility is the wind tunnel. So we have to look into concept development, specification, and look into the budget. And then this is quite a very interesting when actually during that time when we never have a proper lab facility, when we really plan during that time under aeronautical group, which I'm part of the team, and you can see Professor Suhaimi, Prof. Lotfi, and everybody else also under that aeronautical group. We want all sort of things to be as part of the Aerolab. Even in the aerodynamic test facility, we want wind tunnel, high speed, low speed, supersonic, everything, including just now somebody mentioned about shock tunnel, shock tunnel, shock tube, and hypersonic gun tunnel, all these sort of things. Name it, whatever. We always want it because we thought during that time, as an Aerolab, we want everything. So within the budget constraint, of course, we do not want to have everything. So the budget approval process during that time, 1995, when we planned under 7 Malaysian Plan, we start in 1995. Fortunately, we are pleased that the budget was approved about equivalent to about 30 million plus during that time, which is in 1990, mid of 1990s. So we struggle to get now to understand what need to be done more detailed. For example, with that sort of budget, because of the experience, we are lacking of experience. We do not know, of course, based on very limited experience. We want everything just now, but we start talking to the people who know about wind tunnel. So the nearest to us is actually the LAGG Indonesia, where just now was presented by Dr. Anton there. So we work together with them with their help. We visited them and then start talking. Then we know better about what we really needed as a wind tunnel in this case. Okay, so we identify who are the suitable wind tunnel designer and so on. So I would say during the planning type of 1999, this is really the time where we really have to put so much effort in planning and what to clearly identify what we really want. So one thing that we learned later on after talking to our advisors and people who really know about wind tunnel, because the biggest wind tunnel around within our region during that time is the LAGG Indonesia, 4 meter by 3 meter wind tunnel. We understand that first of all, wind tunnel is not custom made or not on the shelf item. It's a facility. You must treat it. It's not like a equipment, but the whole thing is facility. It's custom made and built for specific purpose, and not on the shelf item. So once you have clear this one, then you ideally during that time we want wind tunnel that can do everything, one single one to do all sort of testing. But after we learn a little bit about what putting out the performance-based specification, we look into our mission and we well define what is our mission and test requirement. Basically, our test requirement just to support, as mentioned just now, to support testing and laboratory teaching of laboratory teaching and research in the aerodynamics and related area, and the testing service to industry. So these are the two clear mission and objective of having this wind tunnel. And what to test? Of course, we want to have a wind tunnel that want to test everything. Because we are in aero, we want to test the aero test related aircraft model, helicopter, UAVs, ground, name it. We want to do all sort of testing. On top of that, also from our wind engineering people, we want something that has non-aeronautical related work, which is maybe is just a wind engineering as well as automotive maybe. So it's always a conflicting environment, conflicting requirement in this case. So once we define what is testing requirement that we want, then we have to specify what would be the ideal test section size, what is the maximum wind speed that we want, what flow quality that we want, what sort of power requirement that we expect, what sort of configuration test of test section that we will be having, whether it's meant for the general testing or open type or closed section or things like that. What sort of test measurement and equipment, what would be the computer and data acquisition or instrumentation, and whether we have a special features like having the heat exchanger and cooling system for purpose of maintaining the Reynolds number. So all these things are part of what we learn when we start talking to the advisor. And for this purpose, I would like to really appreciate and acknowledge the support of especially from the technical advisor LAGG, which is Dr. Anton, led by Dr. Anton, Dr. Andy Eka Sakia also is here, and Dr. Sujatin Wiryajaya. Okay, so this is what we learned during that time. So another pictures that we showed just now, we look during the planning process, various options available during that time. How we're going to approach and build the wind tunnel, the concept development, whether the general purpose of wind tunnel, I mentioned just now, putting the requirement and specification, the budget approval process, and manpower and resource planning. Dr. Anton mentioned this morning that building a wind tunnel is important. It's just not that difficult, having a wind tunnel. You can have it in 2 years' time. But to plan for the manpower, the type of testing, resource planning, and so on, that's also important. But once you build wind tunnel, you cannot change for the next, 20, 30 years. You can see the wind tunnel will be always like that, in terms at least physical. So we went to various places, including looking at the biggest wind tunnel also in China during that time, China Aerodynamic Research Development Center, CATC, in Xi'an. Together with, during that time, you can see the photo there, not very clear, but Prof. Anton and Prof. Suhaimi was there with me. So we spent during the winter of that thing, very cold. So we look at their big wind tunnel. And also we identify during that process, we identify who would be the designer and contractor or vendor for this project with UTM. Need to go a bit quickly, yeah. I got about 5 minutes time left. Is it, Prof. I know.
Yeah, not more than 5 minutes.
Not more. Okay. I'm about halfway through.
Maybe 3 minutes.
Okay. So this is a construction stage during that time. 24 months it was completed. We built it under design and build turnkey contract. So this is during that time. The construction stage, I saw that old photo of Prof. Suhaimi and even Dr. Saibuddin during the construction with the project manager during that time from ILOS, Canada. And this is a quick construction during that time. We built the steel circuit are all here from this country, but the rest of the component coming from this photo there, the heat exchanger installation, if I'm not mistaken, or can't remember now, 20 years ago. Oh, actually, this is honeycomb, maybe, yeah, honeycomb. So this is the wind. So looking at the specification just now, I think I don't want to go into technical. After 20 years, I tend to forget. But the number, as what mentioned just now about the flow quality, is comparable to, because we're the same family with ENW Germany, as well as the LEGG, the grandfather, the father, and the son, as what mentioned this morning. So these are the number during this number of during the commissioning of this one. So this is the overall. It looks how big you can compare the size of this one. So once we fix this one, you can see the total circuit of this wind tunnel, which I believe it will be maybe explained later by next presenters or the head of lab. But just want to see the S section is 2 meter wide by 1.5 meter high. So the reason, for some reason, is always tired. People ask me why it was being selected. Of course, we have technical criteria, but it's always, they said, is the height of the first head of the lab. So 1.5 meters. So everybody else has to bend down except me. I can probably stand up straight there. And this is old photo during the installation. And then 2001, 20111, about 10 years after that. Even I got opportunity that visit by the BMW chief aerodynamicist, Hans Gensboom, also visited there. See, he has to bend down there. So while myself and Suhaimi have to bend down a little bit, but I'm still okay in that case. Okay, so we'll do the testing and part of the training and development overseas as well in the related similar facilities. One of them is in NRC Canada, and also one of the important when we plan is that we have a post-commissioning services where having the wind tunnel is one thing, but to develop a proper testing technique is also experience in the testing. That's another thing. So during as part of the support service or expert service, immediately after operational, we have a expert service coming up and help us to develop a test technique. One of them is the head of the NRC during that time, during Steve Zahn, and also some people from automotive expert, Kevin Cooper, I remember one of them. So during the construction, I think it's okay. During the operational part, 2001 is start operational. And the operational, I think we look into developing, as I mentioned just now, developing testing technique, post-commissioning, expert service, and so on. And quickly on the, we did during that time when I was still around, the earliest test that we do is also in automotive. So this is a quarter scale of a model, actual model by Proton when they come. So we develop testing technique during that time, only flow visualization as well as the force measurement. A few developed testing technique that we need flow visualization, the white dot there, everything that we learned from Canada, from others. It's very interesting technique and everything that we learn. And also one of the earliest tests that we do is just the scale model of solar car, and then we did the comparison with the CFD. I think if I'm not mistaken, Dr. Toludin was doing the CFD. Then we do some comparison tests of this one, even though it's not, this is part of our familiarization of this one. Wind tunnel is something that once you put, you can see smoke test earlier. Always, I remember some of the wind tunnel experts that told me, when you want to impress people, especially your boss or decision maker who will pay you the money, just show something that they can see, which is you show the smoke, very nice photo of smoke and so on. They will be happy, then will give the money. Even though we know very well smoke is, nothing much you can see except for qualitative measurement or something that you can see. So one of the milestone during that time, he was accepted as the SATA Subsonic Aerodynamics Testing Association in 2002. And as mentioned by Dr. Anton, it's not easy to be accepted. We are particularly proud to be accepted this one. We have myself and Suhaimi went to do the presentation during that time to convince all these experts in wind tunnel to accept us as part of their wind tunnel fraternity. Okay, I don't want to explain too much on the critical issue and lesson learned. We learn a lot in terms of transport technology, project management, and we know that, as mentioned earlier, the wind tunnel is not just doing a wind tunnel alone, developing testing technique and its integration of all the system and all engineers. It's not meant for the aero people only, but the integration for all the engineering discipline that's related. Okay, people ask me also, what is given a second chance? What if I were to do it again, the wind tunnel, what would you advise? Of course, in Malaysia case, I think national wind tunnel facility and dedicated towards automotive and wind engineering is probably something that we should look into in the future. Because aeronautical, what we built, the aeronautical, I think we are okay with what we have now. But having the country produce automotive wind tunnel with industry of automotive and so on, having a full scale testing of wind tunnel is always an advantage. So I don't want to go into further in this one, but in fact, at one time I was asked to do a presentation at Proton and this was presented at Proton while Professor Suhaimi also was there at Proton during that time. So from dream to reality, what I say is dream in 1985, I was doing the wind tunnel testing of the Delta Wing when Professor Miao present this one earlier on the wind tunnel, the aerodynamics of the Delta Wing and so on. It come back to my memory because I'm doing that. Without the PIV during that time, it's only pressure distribution, 200 pressure tube using the old Scanivaf, old rotating Scanivaf, while now people are using the very fast acquisition electronic pressure transducer. So it became reality. It's part of our dream, not only just my dream, but the whole aero panel, aero group in 2001 is a reality. So thank you very much. And I would say this is another one of my favorite photo. I always remember this. And I would like to say happy 20th anniversary to Aero Labs, Dr. Shabuddin and the rest of the team. I wish you all the best for Aero Lab. Thank you very much for listening. Thank you. This is my acknowledgement.
Thank you.
Thank you very much, Engineer Khair, for the presentation, and we really appreciate your contribution towards the setting up and running of the wind tunnel and aerolab in the beginning. Now, there is a slight change in the itinerary. Instead of having questions and answer after every presenter, we will do the question and answer after all the heads of labs have presented, so that the questions can be discussed between all 5 of them, because this is around the same area. So we move on to our next ex-head of lab, which is Professor Dr. Muhammad Nazri bin Ja'far, who will talk about the diversification of aeronautics research at Aerolab. Now, Professor Muhammad Nazri Ja'far has a long list of CV, but I'm not going to read everything. He's got his first degree and master's from Wichita State University, and he did his PhD in University of Leeds in United Kingdom in 1997. Okay, he has been the Dean of Transportation Research Alliance, Director of Institute of Vehicle Systems and Engineering, Head of the Department of Aeronautical Engineering, Head of Aeronautical Laboratory, Head of the Gas Turbine Combustion Research Group, GTC-RG, and Chairman of UTM Book Panel, and Chief Editor of Journal Mechanical, which is a journal for mechanical engineering in UTM, and a committee member of National Aerospace Council. Okay, I think without further ado, I would like to invite Prof. Muhammad Nazri to give his presentation on the diversification of aeronautics research at Aerolab. Prof. Nazri, please.
Thank you very much, Mr. Session Chairman. And Assalamualaikum to all, and a very good day, because I cannot say good morning or good afternoon because everybody is from everywhere throughout the world. It could be morning somewhere else, and it could be, already night time. So thank you very much. So I took over from Engineer Khair in 2003. I think that is when he was leaving UTM at that time. Yeah, he took early retirement and to go to the industries, and contribute over there, which is, I think, is very good so for our, staff. So I didn't manage to finish my term actually, the second term, which is up to, it should be up to June of 2007, but I was at that point of time was appointed as the head of the department in January of 2007. So I managed to, manage Aerolab for 3.5 years. But during my tenureship, I managed to do some good, some important things also during my time. Because I'm not from the aerodynamic background, so I do not involve much in the in the testing and consultancy work, but I'm more on the management side. So during my time, I think I managed to secure some grant, some money for maintaining the equipment because it had been used for like 3 or 4 years. So we brought back the original contractor, ILOS, to UTM to do the maintenance and also recalibration. And the second thing that I did is actually to to diversify the research at Eurolab. So luckily at that time we got another the second, I think, during our working at UTM, the second IDB loan, I think sometime in 2004 or 2005. So UTM got some allocation of money. So we are supposed to buy several equipment, and then I used this opportunity to actually try to secure some allocation to extend Aerolab, because the Aerolab at the time, as Engineer said, just house the big tunnel. I mean the big circuit, but the other the other research, the other discipline of aeronautics were not put into that Aerolab at that time. So we need the the space so that we can have other discipline, others they can occupy inside the lab. Okay, so this is a aerial view of our. But this one is actually already with the extension. If you see this one, this is the original. The blue actually is the original building, which housed the the low speed tunnel, and this is the extension. And we have several annex to this building, where we actually complete all the what can I say is discipline under aeronautic. Okay, the bottom one actually is the circuit from from the main door. You can see a very nice angle there. That is our wind tunnel that we could be proud of, because I think in Malaysia we were the first to have this kind of facility. Okay, these are some of the. This I borrowed from somebody. I don't know who's I think maybe Dr. Shahudin punya presentation good. But this is to show most of what we have done. But I think there's a lot more that have been done, including our national motorcycle, Morenas here. All right. And this one tak tahu kat mana ni. So ayam bumbung ni kat mana? Tak ingat lah. This is the one showed by Engineer Hay just now. And so many others actually. This is the bridge, I think, was done. The one across the Putrajaya. I think you can see that one. They call it the suspension bridge. Okay, these are the areas actually under aeronautical engineering. But at that time, we only have the aerodynamic only facility. So the rest we haven't got yet for aircraft structure, aircraft propulsion, flight mechanic, and so on and so forth. So that is where I take the opportunity to try to expand the aerolab, the existing aerolab, which only housing the aerodynamic facilities. We have other facilities also because we have the money from the loan, so we need the space. So what we did actually is to get more of the equipment. So in 2005, I think we got the IDB loan. So during the processing of this procurement, so we do the extension like side by side, in parallel, so that when we get the equipment coming in, we already have the the space or the place where we can put them. All right, so there are several facilities inclusive with this. We don't only have the extension on the side of the building. We also have other annex building like the rocket propulsion, combustion facility, and also hangar for the helicopter research, which is now being utilized for the UAV research. So by having all these facility, almost all discipline under aeronautical engineering has been established. However, all this research discipline has been expanded by the by the staff themselves when they have more money from the from the research country, so they can expand buying more equipment, and then some of them they expanded and they moved elsewhere. The process for the session took several years or so. I think it should be 2 years, but I think it was handed over to us a bit late than was promised. We got the building, I think, in 2009. That was handed over to us. I wasn't the head of lab anymore at the time. I was the head of department. At the time, I was involved in a lot of meetings, with the top management of UTM to procure the, to secure the money. It's not easy to get money from them to build this extension building. We have to go up and down several times. And then I have to have several meetings also with the consultant, with the contractors, and also the progress meeting to see that the construction is going through, as planned. So this is the only possible after several series of different. Okay. All right. So we got the one in the 2009. So it's enough time for us to do the ICT for all the equipment. We got several big equipment at the time also. Okay. So thereon, all the research for all the areas was carried out there. We can see so many of the staff, doing the research at in the Aero Lab. Okay, so when we are starting the, the meeting on where to do the extension, so there were several proposal was being given to us. So one of them is to have on the side of the original building, and other one is to have two, because this is a two story. This is a one story on the side and one story in the parking lot. So that will actually take away our our parking lot, and the other one have to have the two story in the parking lot. There is also the propulsion lab for the rocket down here. So we decided to go with option one, which is a two story on the side. We started in July of 2007 until 12 March. But I think this was the one that has been planned, but we didn't get it on the 12th of March. I think it was a bit later. So they have an extension building beside the original. So I should just know here, this one. And then the propulsion lab, which is at the bottom there, and also the hangar. The hangar is actually separate. It's near to the Padang Kawat, where there's actually open, a bit open over there. Okay, the construction process. Here are some of the photos that are taking place outside, inside, and so on and so forth. I just came through here. These are all the different room. So each room will actually have their own function. So like one of them might be for the gas turbine, one might be for the flight mechanic, one for structure, and so on and so forth. So we have both floor, the ground and also the second floor. This one I think might be for the gas turbine because they have this exhaust here, extractor here. The one on the left. This one I'm not sure which room is this. So that is actually during the construction. So this is the one that is already ready that we can use. You can see also the top part of this. I mean the roof actually. The rooftop actually is also being used for some kind of a research, especially for the antenna and also for the, I think for the solid rocket. I think they're doing some testing up there. I forgot already the use of this one. There is a function of this particular thing here for some kind of the way my colleague can actually update later on the use of it. Okay, so these are all the buildings that I mentioned just now. The one for the propulsion lab, we have one main lab here. This one was under the construction, but these two are being obtained or secured by the researchers themselves under their research grant. This is the extension to the liquid propellant rocket facility. Okay, I think this one for the antenna on the top, on the rooftop. These are some of the some of the facility that we have in the extension building. This is the hangar. This now they've been taken over by our friend there, who's doing UAV, Dr. Nazri there. So those are his team there. So it's very they are doing very good job in the all this UAV development. Okay, within the extension building, this is our plan at that time. So we move the one that engineer here was talking about, the blue, we call it the blue and the yellow tunnel. We got to one is suction and the other one is blower type. And yeah, we got it from I think Singapore Poly. I was the head of lab at the time. So the head of lab actually there are two era actually, two era. The one that we talk about here, where engineer here was the first, is the one that we have the building now. But before that, there were so many other head of aero lab without the building. So I was one of them. So there was in 1991, I think, until 1993 before I went for my PhD. So during my time at my tenureship, I was the one who brought in the the blue tunnel from Singapore to be used by by UTM because they know that we have this aeronautical engineering program. So it's placed into the extension building. So this is the extension building, this part here. You can see there are room for gas turbine, there are small rocket testing, PIV, UAV, and then we put the tunnel somewhere inside the first floor. I mean the ground floor. So actually this is where the wind tunnel was before. It's actually in the corridor of this thermal lab because that is the only place that can we can put that kind of facility because it's very long. So we put it there, we do some testing. I think a lot of testing has been done, especially the consultancy work with our client who was doing a gas turbine screen. I think engineer here was the one involved before and then I took over also. And this one is actually located in the fleet mechanic lab. So both of them, we have to transfer back to the new facility because they knew that we have the building, so they want us to put the inside the new. So we put that inside the new building. I mean the extension building to the aero lab. So then we have the UAV lab also downstairs. Now move to the hangar. We have the PIV test room where we have the PIV there. Can do some kind of flow visualization test using the the PIV. This is the structure lab. Most of these are being used by the third year module lab, lab module. So that's why we need this extension because we can house so many of the other discipline under aeronautical engineering that can be used for teaching, for research, and for consultancies purposes. And this is the gas turbine. We got this one. I think this is the most expensive equipment that we got under the IDB loan. The gas analyzer plus the gas turbine, the small gas turbine. It's being used also for teaching and also some research purposes. This is the machine shop used for machining. That means that we don't have to go to other buildings at the main building where at E02 or E01. We can use our lab, to do all the machining. Okay, so we have all the important machine like the milling, the lathe, and so on. So it become what I can say as a one-stop center, which is very good for for the students, for the staff, and for everybody. Okay, the second floor house the avionic lab, and then the computer lab. We have the design studio, and also the flight dynamic lab, which is also our simulator is there. Actually, the design studio we don't have before, so all our students have to go into the the studio at the main building, which is at C25. But now they can just go to the second floor of our building, and they can we have the class there also, and they can do their work inside there. So this is how it look like. So this table we can split them so that they can use it as a single table, or they can six of them can sit together during the class, the class time. So this is how it looks like. Okay, this is the design class, and then this is the computer lab, which is used. Before we don't have this. We have this one, but a small room on the main building. But now we move everything to this more comfortable room in the extension building. And then this is the avionic lab in the second floor. This is a flight simulator room. It's all equipped with our our simulator in there, which is very nice. You can see there. And the rooftop also being used for testing. I mean that we utilize the whole extension building to the most, and all the discipline and the area of research has the opportunity, to use the Aero Lab. So now Aero Lab is not only for the aerodynamicists, but also for other, for other, what do you call it, discipline. Okay, so by that they all can come under the same roof and do all the supervision for the student, and then do the research, get out the research, and we do some consultancy work. It's not only confined to the aerodynamics, okay, discipline. So that gives a lot of opportunity to everyone to sit there and do discussion. So that make all of them are, I think, at that point of time very close together, and working as one. So I think that is my major contribution when I was the head of lab. So I felt quite quite satisfied and proud of it, so that I managed to go up and then talk to the top management that we want this. If not, you're not getting that, you have to fight with them, and the fight until the the last breath. So Alhamdulillah, everything was being obtained. So we can do the teaching for both undergraduate and postgraduate. We can do research, consultancy, and so on. So actually, the Aero Lab after that become livelier than before, which is only occupied by the aerodynamicists only. Now everybody's there doing their work, and have a tea. I think they have a tea in the meeting room. I think so we can go there from time to time and sit down and discuss anything under the under the aeronautical problem that we can talk about. So I think that was the last. Oh no, there's one more. This is during my time. So I think this one we did go to Langkawi, Lima for I think 2 or 3 times before my before I stepped down. So these are all during the Lima, where we met a lot of people like the Sultan of Brunei and the Dan Agong, I think from Perlis, and our current Queen also, Queen of Johor. At the time she was the, I think, apa dipanggil ni, Raja Muda? I forgot
Princess.
already. Princess. Okay. Consort. And this is during the opening ceremony in 2005. So I was the head of lab at that time. You can see Mr. Ainul there. Look really tension there, I think. So that's it. I think we will have the question later. So I'll give back the floor to our MC.
Okay, thank you very much, Prof. Nazri, for the presentation, highlighting what sort of developments that have been done after the lab has been established. We move on to our third head of lab, which is Prof. Engineer Dr. Suhaimi bin Mansour. Dr. Suhaimi received his PhD from Labra UT. He's one of the first batch of aeronautical engineering students from UTM. He did his diploma and degree in UTM. No, he did his diploma in UTM. So he's a pioneer in terms of the aeronautical engineering program in UTM. Got more than 30 years of experience in teaching, research, and design projects. And he has work experience in British Aerospace for 1 year. And also, he's been in Proton for 3 years, becoming the Proton professor there before coming back to UTM. And currently, he's the assistant dean for external and global engagement Faculty of Engineering, University Technology in Malaysia. So I welcome Prof. Suhaimi and hand over the forum for him.
Assalamualaikum warahmatullahi wabarakatuh. Very well. Morning still, yeah. To all, to everybody here. Thank you, Prof. Anur Lutfi, for giving me this opportunity to share my experience with Aerolab development, coincide with our 20 years anniversary. So my title today will be on the appreciation of wind tunnel design, technology, and applications. So as Prof. Nazri mentioned that we have two era, yeah, Prof. Nazri. The first era that we don't have the
facility
building, the facility yet. So we have only small tunnel. During that time, the first era, I was the head of lab from 1988 to 1990. So after that, I went for masters. I think from that time, Professor Nazri.
I think I took over from you. Yeah.
Yeah, that's right. Yeah. So that's the first era. Then the second era, when I came back from PhD.
Then you take over from me.
Yes. And again, I took over from you from 2007 to 014. Yeah. Yeah. Thank you, Prof. Nazri, for your, what we call it as this thing. We separate into two era. So then we realized that we start the aero since the program started a long time ago. Yeah. I just would like to give some introduction. First, the meaning when I put appreciation. Why I put appreciation? So if we refer to Oxford Dictionary, so appreciation meaning the recognition and enjoyment of good qualities of someone or something actually. So that's personally what I felt during this development of Aerolab. And secondly, a full understanding of a situation and increase in monetary value. So if we can experience this, I think it's more sensible for me to use this word appreciation. So to conclude the whole what I felt during the development of Aerolab, I can say it's a bittersweet memories actually. Yeah, there's some hurdles, some problems, some issues, but we managed to overcome, and then we come up to this stage. For me, is really a bittersweet memory because during the started of the lab, we have a family, we're growing a child. I remember that my third baby born. 2 weeks after that, I left for Canada for 3 months. So when I came back, she already can sit down. Yeah. So that's really something that touched me. So in terms of appreciating of the project, I can divide it into three main things. One is the design itself. Second is the technology, and third is the application. When I say design, what I appreciate in design, because in the design we have so many parts, so many components integrate each other. So they are all independent. They're all dependent. They are dependent each other. So for sure that during the development of the lab, they are all become conflicting issues. So the B2 is to solve the conflicting issue is by compromising, but actually it's not easy to compromise. And I think I have to be honest that yes, and Engineer K, he lead the project, but for the technical, actually he passed to me actually. So I have to look into the great details of the engineering design of the wind tunnel, and with the team from the Aero Lab, we managed to make things come true. So secondly, about the technology. So throughout the project, I realized that because I start from nothing, I start from zero. Yeah, I realized that the more I learn, the less I know. Because when you learn something, you found out there are more things to learn. There are more things to know in order to get better. So it doesn't stop me to self-learning, because the more I learn, the more I don't know, then I think I need to learn more actually. That's my appreciation about the technology of the wind tunnel. Lastly, about the application. Many people talk about application. Oh, what do you apply with the wind tunnel? What do you want to do with the wind tunnel? Does it going to be a white elephant? But for me, summarize the application is about progression to survival actually. Yeah, it's not easy to sustain and to survive with the facility, because I still remember that when we had the facility, we can hear that some people that in one day it's going to be a white elephant. So I put in myself, we are going to progress this. It's going to be flourish, and one day we're going to be center of excellence. So that's a little bit about the introduction. And then when we focus about appreciation about the design, what I learned a lot is about project management and the strategy. As a design project, we should have one mindset. We have to put a mindset. First, as Engineer Kim mentioned, that wind tunnel is a testing facility. It's not a tools or equipment. You can have a wind tunnel with the wind blowing, but if you don't have the equipment to support that for the research or for the serve to industry, you won't get a good product from the wind tunnel. Yeah. So another strategy that we have to go as the best equipment with the best price. This is I learned from our friend from Indonesia. Best equipment with the best price. Because normally when you bid a project, there's a tendency that people will take the cheap one. Yeah. Most likely they're going to take a cheap one. But now you have to justify the cheap one is not fulfill the requirement of your facility. Yeah. And of course, during the design, we need to have a provision for future development. And remember that this is the engineering design and system integration. It's not one field of expertise. It involves many areas of expertise, because in our wind tunnel, I think we have 12 contractors involved in the design and build of the wind tunnel. So yeah, first word I put it right is testing facilities. Yeah. And then performance requirement. As a performance requirements, the design should meet the ETM requirement, and the flow quality is a world-class flow quality, because we based on the DNW wind tunnel here on the left here. This is a benchmark wind tunnel, and also from the ILST. And these two wind tunnel actually been built in 1980s. Yeah. And our wind tunnel in 1990s. Yeah. So when I put the stringent flow quality, it's another thing that I learned from our colleague from Indonesia, that first of all, we put the flow quality of the DNW wind tunnel, which is 1980s. And I remember that Pak Andi discussed with me, Pak Suhaimi, Why don't we put more stringent requirement? I said, why? They might have a difficulties to fulfill our requirement. And Pak Andi positively answered my question. He said that now we are in 1990s. We want to know how the technology has been advanced. What are the new methods, new techniques that can improve the flow quality? So that's really something that also really I appreciate of that. I need to learn more. I need to study more, whether we can achieve the flow quality or not. Yeah. And finally, to design requirement of the facility. So you can see that here the benchmark wind tunnel, the NW, the test section size is 8 meter by 6 meter. Yeah. And here this Indonesia low speed tunnel, the test section size is 4 meter by 3 meters. And this is the Sun, yeah, UTM wind tunnel, the test section is 2 meter by 1.5 meter. If you can look at this, yeah, so the test section size is basically we are half of the ILST and half of the DNW, and I see half of the NW. Yeah. If you look at the airline circuit of the tunnel, it's almost typical actually. So that's why we declare that yeah, this is our father, this is our grandfather, this is us actually. Yeah. So another thing that I learned appreciation about the design is the knowledge and the design freedom. So at the beginning of the project, we do the conceptual design, followed by preliminary design, detail design, manufacturing, and testing. So at the beginning, our knowledge almost zero, especially for me. Yeah. So I need to learn a lot actually. And then the design option during the first time, so many options. What kind of tunnel we want to design. Yeah. But as we develop, we try to customize our design. And then as the project progress, the design freedom become less and less. We know what we want clearly and precisely. And you can see that the knowledge actually increase throughout the process, time into the design process. Yeah. So we gather all the knowledge, and then we know that during the design we have to refer a lot of reference. So I still remember that we always refer to Jasma is one of the author for the DNW wind tunnel design. I still have the papers here. This is some of the picture taken from that papers, and we also refer to Barlow wind tunnel testing as well, because there's some design analysis also in that book actually. So then, as appreciation, design knowledge and experience, as we know that for the flow of the process, we have the conceptual design, which involve system requirement, system facility, then preliminary design. We have analysis, detailed feasibility analysis, and preliminary design. And then until we goes to detailed design, construction, commissioning, and operation. So during the conceptual design, actually, because we have experience with previous tunnel, especially in the IST tunnel. So basically, Pak Anton already talked about operation during the conceptual design. Operation and maintenance. Yeah. So meaning to say that during the design, we already has a provision to make us easy. For example, to clean the screen, yeah, to clean other parts of the component, because that the maintenance, and we have to think about provision for modification or improvement for the future. Yeah. So the parts that component that really involved during that time is the wind tunnel test section, pen drive system, flow straightener, which is honeycomb screens, balance support system, heat exchanger, and data acquisition and reduction system. So interesting thing that you can see that as the knowledge increase, sometimes we think that we are smart. This is very dangerous, because when we gain some knowledge, when we work in silo, we think that we are smart. Actually, not really. When you actually go expose yourself outside, then you know that, oh, there are many things that we need to learn. There are many things that we need to know. It's basically it's not easy to become expert. Yeah. So yeah, as a technology, we learn a lot for the manufacturing, assembly, and testing. So again, heartfelt thanks to RST team as technical advisors, introduced by Prof. Afifi. So I still remember that Prof. Afifi mentioned to us that we go visit Puspik Tech in Indonesia because they have a wind tunnel there. So then we have communication. Mr. K, Mark K, Engineer K make a communication, and we managed to visit the facility. Basically, for me, it's really an eye opener for my project. Yeah. So this is our circuit. Why I put here because we our circuit made from metal. Yeah. But the LST circuit made from concrete. Yeah, so that's something that we have to customize with local expertise as well. So thank you to Prof. Dr. Anton Adibroto as the head of LEG during that time, Dr. Sujatin as the assistant, and also Dr. Andi Eka Sakya. And as the training, we have some experience, expose real hands-on training about the testing technique, blockage correction, trap interference, data reduction system, model design and making, and instrumentation and control. And as a technology, we are thankful because we are guided by world-class experts. You can see that people, I think Professor Barakos is here. 15 years ago, he came to visit our tunnel. And Prof. Nazri here, Prof. Nazri, still young, and Pat Field, and me inside there. And here we have Kevin Cooper, who is from the NRC. Kevin Cooper is trucks aerodynamics and automotive aerodynamics. Here is Dr. Sabudin, supervisor here, right?
Yes.
So also visited our tunnel. Yeah. And interesting thing, during this networking, I managed to meet Barlow, Joel Barlow. So he's the guy who wrote the book of the wind tunnel. So when you manage to talk with these people, so you feel, I mean, confident and comfortable and discuss about your wind tunnel performance. This is during the SATA meeting actually. Yeah. So then the rest we some photos just how we actually been trained and been customized the kind with our wind tunnel. So then goes to the application aircraft design. So this wind tunnel originally dedicated for aeronautical testing. Yeah, so that's I still remember that because during the development of the design, Mr. Ratko Joya actually precise me asking, what do you want? You want to pitch from what angle to what angle? You want to yaw from what angle to what angle? Because he want to design the other support systems. So then we focusing on aeronautical testing during that time. But however, in Malaysia, we have aircraft industry like SME, which MD3, CTRM, but it's not so flourish. So sometimes we have to think of how to survive with the wind tunnel that we have. So without the or less support from the aircraft industry. So we have to spin off and diversify to other fields, for example, like automotive, civil structures and building, oil and gas, and offshore structures. So luckily now the emerging of drone application, so we got more job and more things to do with this wind tunnel. Application for automotive, I think this is Engineer K already share with us about the automotive. Just what I want to share here that first, the automotive testing, we only support by a single strap here. And then we support a span here because we don't want this tire attached to the floor because it will be a tear effect, meaning the load that you measure already wrong actually. So we only have a single strut support. Because of this difficulties cumbersome, we with the technician, we modify the support system of the balance to become 4 posts here, 4 support system. So now the tire can rest on the plate and then the plate isolated from the floor of the wind tunnel, so then we can measure much more easy with the automotive model actually. This is application, civil structures and building. So it's one of the challenge project that we took up from the EduCity Johor. So this is a sports complex here that we test in the wind tunnel, and we provide measurement of surface pressure and wind load to the client. And yeah, this is the real of the stadium after completion. So this is Prof. Anul Lutfi. He's the cameraman. He always been his camera everywhere actually. Thank you for that. We have someone in Aerolab that always like to take photos. We expand our room to the oil and gas and offshore engineering. We modified our wind tunnel with the floor panel. This is not on the original floor. We built another floor on the tunnel because we want to tilt the oil rig about 30 degrees. We don't have plenty room underneath the test section. So we have to build a platform floor. Then we attach to the balance. Then we be able to now turn or rotate or bend, incline the model of the oil rig in the test section. So this is the real test section. Sorry, the real oil rig that been built in MMSC. So this is another success story that we managed to pick up project in the area of oil and gas and offshore engineering. So the idea to be a center of excellence, we already think of since year 2000. I think this is a picture of us when we have a training. Yeah, Shabuddin. Yeah, Dr. Shabuddin. This is in Ottawa, Canada. This is Engineer K, Wan Khairuddin, Dr. Shabuddin, and me. Yeah, so we set a goal during that time to be a world-class facility in education and training, research, innovation, and service to industry. So the most difficulties during that time actually to manage 3 things. Yeah, the people, the facility, and the financial. I guess you all know which one is the most difficult to manage. The people. Yeah. So this is the most difficult to manage the people because, to be honest, that we all here is not full time. Yeah, we are most of us lecturers, and then they have their own focus. Then a bit difficult then for a full time. So, but we managed to handle that, to manage the people for the facility with a good financial stable status. So knowledge expansion, as we know that we started from aerodynamics. To be relevant, we grow for the aircraft stability, aircraft design, we do static tests, then we expand, we do dynamic tests, and then we do some structural, so which is the aero elasticity, and we are looking forward for aeroacoustic in the future, as Prof. Barakos mentioned in his first talk in the morning. Yeah, so we focusing more now on CFD, final element, and the combustion and propulsion also from Prof. Nazri, and energy. So we have a applied aerodynamic research group. I think this is the best platform to utilize the wind tunnel facility. And the major work that we do here is basically to do a correlation between the wind tunnel test, the simulation, especially CFD, combustion fluid dynamics, and the flight testing, the real flight. So if we can do all this correlation, then we as Prof. Barakos said, that we will progress from time to time, and then we know that technology grow, then the tunnel will be improved with the instrumentation and other things. Yeah, my last word is say the taming the wind actually. So we should have a postgraduate research, and I should thank them all because through postgraduate research, we managed to develop the wind tunnel until today actually. So here is Dr. Iskandar, actually my first PhD student and the first graduated product from the wind tunnel actually. This is Basit, our engineer, wind tunnel, and the rest is all my PhDs and master students. Yeah, that helped me until I become to this stage actually. So the future challenges, of course, that we have to think how to reduce operation time and costs, living in the tight budget, staff competency, innovative and creativity, and sustainable facility. These are the things, the keyword that I think we need to hold in order to sustain in the future. So if given a chance, as it's Kay mentioned that if I give a chance, I want to have a roof turntable and for model support system because we have a problem to do a tear with it's a complex how we call it comprehensive tear, and then possible to have open jet testing facility, and then test section number 2 maybe focus on aero acoustic and PIV systems. Staff, with in the future we must have a staff that good in system integrator, programmer, data scientists, and then staff that very good in vibration, noise, and acoustics. I think that's all from me. Thank you very much. And again, congratulations to UTM Aerolab, and thank you for the 20 years anniversary. I pass back to Anul Lutfi. Thank you, Anul.
Thank you very much, Prof. Shohaimi, for your excellent presentation. Very insightful. And I think it's a good sharing for not just for the UTM people, but also for everybody involved, because they can see the mindset behind what we've been doing, and maybe there is something that we can share, inshallah. Okay, we move on to our next presenter, who is Prof. Wan Khairuddin Wan Ali, Prof. Dr. Wan Khairuddin Wan Ali. He received his Bachelor of Engineering double degree honors in Mechanical and Electrical Engineering from University of Tasmania, Hobart, Australia, and Master of Science and PhD degrees from Cranfield University, specializing in avionics. He's a professor, one of the earliest professors of the Aero Group, with 25 years of experience as academic researcher and practicing engineer. He's got two main areas of specialization, which is in avionics and instrumentation, as well as in propulsion. And he holds 5 patents, published more than 100 technical papers, and he was presented with the Shell Australia Award for Best Subject Performance and GE Avionics Award for Best Master's Thesis. So over to you, Prof. Wan Khairuddin, for your presentation. Thank you very much.
Thank you, Mr. Chairman, and thank you to all Aerolab team for inviting me to give a few seconds. Thank you, everybody. A very good Assalamualaikum and very good afternoon. Yeah, or for Malaysian. Yeah. So can I share my slide? Yeah, I try to share my slide. Wait. Have you seen my slide? Have you seen?
Not yet.
Not yet.
Not yet, bro.
I think we have a problem with your line. Prof, maybe if you stop your video and you just present your slide, because there is a problem with your line.
Let me call him.
Ya, macam lagging kan tengok.
Prof Wan, can you switch off your camera so that the bandwidth is being saved, and then just present, because your line is very bad.
Okay, I try. Okay.
Okay.
Already
Better,
saw my
better.
video. I try to share. The only thing is
Okay.
I'm at home. Okay. Let me see. Okay. Let me see if I can give you this one. All right. Can you see my slide?
It's it's starting to load, but it's not up yet.
It's uploading now.
Okay.
Belum.
Okay.
Keluar, masuk balik ya.
Just tell me if it's already on. Belum lagi. Oh, what happened?
Okay,
I'm supposed to be in.
Okay, it's up.
Really, I'm supposed to be in Aerolet, but okay. Thank you, Mr. Chairman. And can you hear me? Is it okay? Can you hear me?
We can hear you. Yes,
All right.
yes.
Yes, Prof.
Okay,
Can
thank
you
you very much.
turn the presentation for mode?
Okay. I try. Okay. Let me see. Let me see. Presentation. Wait. Okay. All right.
No,
Okay.
we don't see that. Okay, yeah, we got it.
Okay. Thank you very much for your patience. I apologize because I at home and the internet line is very terrible here. That's why I'm always in Aerolet all the time. But anyhow, we try our best. First of all, I would like to thank you, Mr. Chairman, Assistant Chairman for introducing me. And I joined, become head of lab in 2014. I'm taking over from Suhaimi, and I feel that I was lucky. Yeah, they already established the facility. Yeah, and with Suhaimi, the culture, the working culture is there. Yeah, where the staff is already well disciplined and everything. So it's okay, everything is fine. But the thing is, it's about the financial. Yeah, so we need to generate income. Yeah, for the lab. Yeah, why? Because university start questioning. Yeah, they say that the government already have spent about 30 million for the early lab, and then after that, with the new building, another few, I think 1 million or so, if I'm not mistaken. So they request for the for income generation. So these are the things that I have to look into when I take over. Yeah, and some of them, the reason also because of university would like to retain this status as a research university, yeah, and also to improve university ranking and for maintenance. Other than that, we also need the lab need some financial independence, yeah, for maintaining and for maintenance and personnel hiring, yeah. Although the core personnel staff is being sort of uh, uh, employed by university, paid by the university, but sometimes we need extra. Yeah, we need extra staff on our own to help running the lab. Especially, for example, we have one RO that we hire. We specialize in electronics and programming so that we can maintain our own test section, the balance. We managed to migrate from original software using I think Pacific Instrument, if I'm not mistaken, to a more general, more robust software for the balance that is using LabVIEW, yeah, at that time. So these are what we need, yeah. And also we feel that we need the money to assist some of the members or fellow members at the lab to do their research. The money is hard to come by. Our members want to do research activities. So if we can help assist them with equipment, buying for them the equipment, this will be a great help and get the lab can grow, yeah, and make them more attached to the lab. Okay, so these are why we need more or less the reason why we need to generate income. Yeah, and how the income generation timeline in Aerolab. We start from when it start operation around late or around 1999. And 2004 is kind of operating learning and confidence building period, yeah, where we try to learn. And at that time, I also went to NSCR, learning how to operate the wind tunnel, and went to the Serpong to learn also to how to operate the wind tunnel. And we send our people all over the place. And also at the same time, we do in-house training. So that is from about 2000, 2004. So it's a training period. No income actually been generated. Mostly we spend. Yeah, it more or less is a investment. Then from 2004, 2014, we start to generate some income and building the reputation. At that time, from our record, we have on average of about 70K to 100K income generated annually. But there is gross income. When you deduct all the expenses, normally annually we can have some extra about 10,000 to 20,000 to K only to go into the saving of the lab. But even that, we cannot spend it because we need some reserve for emergency. Yeah, for emergency, we need to reserve for emergency in case our fan drive become sort of broke down, all those things. So we need some reserve. So because of that, even though we have some money in the account at that time, we cannot spend it. It's for the reserve in case of anything happen. Then from 2014 and now we start with the reputation or the build, and we have experience, we start exploring new areas of income generation. I'm talking here is about Aerolab, which means that not just the wind tunnel, but other facilities around it. Yeah. From 2004 to 2014, major income contributor is were UTM LST, yeah, and in form of testing, consultancy, academic activities, all those things. Yeah, and then we have also short courses and seminar. These are the major income contributor. Yeah, and then when we start to diversify, yeah, we would like to increase our income. Sorry, yeah. Then we find that we need to identify the potentially income generating resources. Yeah, the first step in identifying potential resources is we have to list it down. Yeah, so the following list are the potential resources, although it's not an exhaustive list. It's it's good start. Yeah, to start with. First, I think is the best thing to know is that networking over the almost 15 years from start of building of UTM LLC until to 2014, we have built up certain networking. And these are the people who come to us to do the testing and then generate our confidence and also reputation. So networking is a resources need to be looked at and to be exploited. Yeah, and they are customer base or client base. So whenever the client come with a problem, is an opportunity. Yeah, for us to solve it and to generate the income. Yeah, so the first thing we need to know is to look at for income generation is look at our networking. It's very important. So the previous lab head of lab has done this very well, really, and they established, especially the one that been done by Encik Khair, IR Khair, and also Prof. Suhaimi. There's a lot of connection, and people come, and we have a good networking. So that is the first resource we need to look at. And then secondly, we have this smaller wind tunnel that we inherit from previous lab. Yeah, we have the blue wind tunnel and also a blow tunnel that we have on this. Yeah, let me see. Yes, this the blow tunnel, and these are not very accurate in terms of measurement type of wind tunnel, but it's allowed special testing condition that we won't do it on UTM LST. In fact, we cannot do it. Like for example, for this blue tunnel, yeah, we do the testing on the filter. And what we do is that we inject debris, we inject water, salt water probably, yeah, and we inject in there, and then sometimes the filter breaks and the whole debris goes straight to the this is a suction wind tunnel, so whole goes straight to and hit the fan. Yeah, but because it's very rugged and very sort of easy to clean everything, so we don't mind testing that kind of condition with this blue tunnel. If we do it on the UTM LSD, I don't think we can do that. We don't want to do that. Would you put water inside the test section, spray water, salt water, and throw stone and debris inside that just to test the filter? No, we won't do that. So there's a condition where UTM LSD cannot do it, but it bring a good income. Yeah. So these are things that we have to look at. Yeah. And secondly, like this one, we can test. It's a blow tunnel. We test a sort kind of oil rig residual gas burner. You cannot do that in the UTM LC where you burn a gas inside the control the control section. Yeah, you cannot do that. So these are this is a resource that we need to look at, and also we need to approach industry, say sort of expose to them what we can do with this. Yeah. Another one is the staff associated with Aerolab. These are the resources. They are diversified in talents and expertise, and that need to be highlighted to the industry. Yeah, the industry would like to know that. We would like to hear from us, what are your experts? So these need to be kind of exposed to industry, so that at the end, Aerolab can be a one-stop center to solve industry problem. If they want to come to Aerolab, anything about the wing, yeah, they have to study of wing, they come. Not just about doing the wind tunnel testing, but also sometimes what they need is just only CFD solution. Sometimes what they need is just to test the structure, which not going to be in the wind tunnel. So academic staff associated with Aerolab is another resource that need to be looked at and highlighted, and can be used, can be an income generation. And we have a short courses closely tied to the expertise and the number of academic staff associated with Aerolab. The bigger the number of staff with various talent and expert, the more variety of courses can be offered. We have done this either with the Sudanese here and a few others who come to learn hands-on trade about wind tunnel, and not just wind tunnel, but also on the computer software and everything. These are the example of the brochure that we have done in 2016, and it can generate income. Yeah. Fifth, I think we need to look into wind loading effect on structure and wind engineering, areas of product and model testing that Aerolab can explore. Yeah, taking advantage of the current trend in civil engineering testing requirement. Yeah, the changing of climate and more high-rise buildings being built, requirement to test the building model in the wind tunnel has increased in research. We have a lot of clients coming, not a lot, but a few, who are talking about testing 80 stories building, stating a different shape of stadium. So these are something that need to look at. Yeah. So wind loading effect on structure. Yeah. And also wind engine. Some modification of wind flow pattern inside the working section of UTM LST is needed. So, but we have the experience, and we can do that. Yeah, this one is we do the testing on the street lantern. We have on the stadium, and it's part of the suspension bridge, if I'm not mistaken. So we can do that. And to modify the flow pattern, we have some experience to do that. And wind loading effect on certain structures such as metal deck, yeah, roof and wall are tested using existing standards and can be done without using wind tunnel. Yeah? One. Second, local manufacturers exporting this product are facing demand from the importing country to produce certification complying with the certain international standard of this on this matter. Yeah, and also we have the reputation of Aerolab as amount local industry related to the anything about wind study means that the industry are drawn to Aerolab for solution. Yeah, so I found that when during my time, industry come to us because we already exposed ourselves at that time, and we all say that we can do this, and to the industry, anything about wing study, anything concerning wing study, Aerolab is the place to find the solution. And we have one that is we have do for this sort of example of metal deck roof. We construct equipment, test equipment to test the metal deck according to ASTM is 1592-05 standard. So for this, sometimes it's not the wind tunnel that is generating income, but sort of a new equipment that we invest that can generate income in the wind tunnel, in the Aero Lab, because of the reputation that Aero Lab has, and we take advantage of that. Yeah. And then how we, when we identify all the resources, yeah, then it's about, we have to manage it. Yeah. So the first thing that when I was a head of lab, when I look at the Aero Lab, because you have to be in mind that my degree and my experience is not in wind tunnel. I'm over avionics. So it's very difficult to think what to do at that time. But anyhow, previous lab, head of lab has helped me a lot. And I look at the Aero Lab fees. Yeah. While all will the fees will always be in the mind of client whenever they come to Aero Lab. Yeah. And I found that when I do the first meeting with the client who come to UTM, to Aero Lab, they always ask, this is the first meeting, how much it costs? It's always like that. So the fee factors are important to be clear up during the first meeting. So from 2000 to 2014, Aero Lab has charged its client a flat rate, more or less a flat rate, about 4,000 per day of UTM LST usage. This is considered cheap at that time. But there's a consequence when you give something that is too cheap. Yeah? Then they perceive that Aero Lab was perceived as of giving cheap and low quality service. Why? Because lacking of confidence and with negative perception arriving from the fees quantum, normally, and it's often the client turn away after the first meeting. So we need to do something. We need to do something about the fees. So managing the resource means also managing the fees. So these are the structure we took in 2014, and we have a range of that, and we bring it up a little bit, the fees, and it works. People have more confidence, and we can talk reasonably. Yeah. Because these clients, sometimes they come to us, they also already do the survey on other facilities. Yeah. So we up a little bit the fees so that it's comparable with others. Yeah. And then we also need to, in managing the resources, we need to exposing Aero Lab. Aero Lab should start exposing its capability to the general public through several methods: publishing, writing article in popular technical publication targeting engineers and industry. The best in Malaysia, normally, if we can go for engineer and juruterus, is there, which is a magazine and bulletin by Board of Engineers and also Institute of Engineers. Yeah. Normally, when the staff of Aero Lab publish in a sort of academic publication, it does not translate into contract or kind of job. Yeah. But this sort of magazine is well known by the engineers, and they are we are targeting engineer from local industry as well as other technical people, exposing Aero Lab capability and service by joining expos and exhibition. Some amount of investment is needed in this case. Yeah. And then networking, we have to manage that through social media. Aero Lab can keep it networking active and grow. Yeah. Require dedicated staff to keep it social media connection active. Frequently connecting former client with Aerolab's activities and news. This is very important. And then normally we need a dedicated staff to do this. Always update Aerolab Facebook or whatever, and always contact the former client if there's any change or there's any new development in Aerolab. Yeah. Then we have to upgrade and new area of testing. Yeah. Aerolab has experienced increasing demand for testing of a product or a model with test specification they are new. We never experienced that before. For example, here we test a dynamic response of ship in UTMLST, where the ship model was required to be placed in a pool of water inside the working section. Yeah, so this is a pool of water there. So you know that we all know that water and electronics, they are not friends. So when we do this, we have to make a calculated risk. We have to design the deck, the new level there, where we put a kind of aquarium there. And if there is a splash of water, it will be safe. So the design should be kind of, if it fail, it will fail safe. Yeah, it might destroy the model and this the pool here, but the rest of the wind tunnel is still safe. So we have to do that, and we have to calculate and do the consideration. It takes some thought in doing this. Yeah, I don't advise those who are head of lab who are not confident in electronics and in a lot of things. Yeah, to do this kind of thing. Only if you are confident enough with your staff, with your workmanship of your staff, then you can do this. Yeah, because the wind come from here, and then at the same time, we kind of a sudden move of the ship to do the dynamic kind of response of the crosswind. Yeah, so these are need to do, can be done, and it's a way to generate income. People are asking for something like this. Yeah, where test specification are new. Yeah, and by the way, this is a better ship being flown straight from France to do the testing here. Yeah, and UTMLST has gained certifications. Yeah, all this we have it's become an accredited laboratory status. Is a resources waited for to be exploited. Then we know that to industry, having a laboratory report on their product from an accredited laboratory would mean a great deals. They can easily sell in locally or internationally. So this is another resource need to manage and need to look at. Yeah. And as a conclusion, I think I take more than 20 minutes. Anyhow, there are many resources existed in Aerolab awaited to be utilized, discovered, and upgraded for the purpose of income generation. Everybody has a role to identify that. And there are even more resources awaited to be created in Aerolab through the proper management of the existing resources. The proper management of resources such as equipment, personnel, office and laboratory uses, spaces, networking, etc. Are the key of a successful income generation. With that, I like to conclude. I want to acknowledge UTM laboratory, aeronautical laboratory for the support and privilege of sharing the accounting data and information about the laboratory. With that, I thank you And I wish to say happy 20th anniversary and wishing all the best to the UTM Red team. With that, thank you very much. So
Okay. Thank you very much,
let me
Professor Khairuddin, for your presentation. We are running out of time here. We'll move on to our next last speaker today, who is Engineer Dr. Shahabuddin bin Mat. He received his PhD from University of Glasgow in 2010, and he's been working on experimental aerodynamics, particularly on delta wing aerodynamics. He's currently the director of UTM Aerolab. When UTM has been raised to the status of Center of Excellence for UTM, he was promoted from the head of lab to become the director of Aerolab. So can I call upon Dr. Shahabuddin to continue your presentation? Thank you very much.
Selalu Azan.
Okay.
Assalamualaikum. Can you see my slide there?
No, we don't see your slide. We see you. Okay, okay. Now we see the slide.
I'm sharing
Yes.
it. Okay, so all fine, all right?
Can you go on presentation mode?
Okay. So I'm a last speaker today. Okay, I'm a last speaker today. So Assalamualaikum and very good afternoon for the invited speakers, okay, guests, friends, colleagues from around the world. Okay, so I will spend on about 15 minutes, okay, to get on how we Aerolab towards COE, Center of Excellence. Actually, COE in Malaysia is given. It should be given by Ministry of Higher Education Malaysia, and also ISO 17025. So actually, always I acknowledge my bosses, my premier bosses, 4 of them. Engineer K, Prof Nazri, Prof Shuhaimi, sorry, Prof Wan Khairuddin. So their hard work, okay, the hard work have made my work easier actually. Okay, so they make my work easier. Okay, so they how the person who established actually the system. They established the system for Aerolabs. Okay, but one word I really afraid most is the word that used by Prof. Shohami just now, is white elephant, white elephant or gajah putih. So I don't want to be, I don't want people say you are the 5th head of lab who make this 40 million equipment white elephant. So I have to work hard actually, okay? But as I say, it's easier for me. In my era, people want to see KPI. What are KPI in terms of numbers? So right, so there is a figure. There is a photo shown also already by Prof. Nazri just now, okay? So this is the route map of Aerolabs from construction until now. Actually, I'm taking Aerolab starting from here, upgrading to research center. Okay, so I'm taking from here, from Professor Dr. Wan Khairuddin. Okay, so again, thanks a lot for them. Okay, so then. Actually, I want to talk 2 things today. Maybe useful for my colleagues in local university or international university on how to achieve COE in Malaysia, and also how to get ISO 17025. For your information, we are lab number 7 in UTM who obtained ISO 17025. So this is the lab that we have. Okay, this is the laboratories that we have here. Okay, right. So I want to show you people just now talking about SATA. SATA, blah, blah, blah. And this is the certificates of SATA members, okay, certificate that given to those who having good wind tunnels only. There are 80 wind tunnels around the world having these certificates, okay. There are, this is, I asked my PhD student to draw this, okay. This is around the world, okay. Those who having, those who are under Subsonic Aerodynamic Testing Association, or we call it SATA. In the region, we are only in our father, Indonesian low speed wind tunnel, and in the Aerolab. Okay, so we want to more. We want to have more people around in the region to join this as this exclusive society. Okay, so I have this is the current photos or the current activities carried out in our lab. Okay, I rearrange photos by Prof. Nazri just now. So some we are also involving with industrial aerodynamics, OTEX project. So I initiate Delta Wing research facility in UTM, UAV. Okay, then also combustion by the other colleagues. This is not me. This is teamwork, teamwork research. Okay, so I will summarize now. I will summarize. Okay, I will summarize on how the route for us to be a center of excellence. Okay, to be a center of excellence. Okay, so this is the evaluations done by a university level. Apologies me, it is in Malay, only this slide, okay. So we have gone through to JK is a community is a committee of in the school on in the faculty. If the school pass, it goes to committee in a deputy vice chancellor. Okay, deputy vice chancellor for research. Okay, the meeting. Okay, we have to defend, me and Professor Pakar. Okay, have to defend this in front of deputy vice chancellor for research. And then it goes to Jawatan Kuasa Technical Dasar. So it is a committee who look into the policy and of UTM. So unfortunately, I have to go through 3 times. Okay, 3 defending time, and I have to defend 3 times. Okay, then until the 1st July, the proposal went to JKDEU. So it's another committee, committee in the university, chaired by Vice Chancellor himself. So it was on 16th of July. Okay, the proposal went to Senate University on 29th July. It's not easy to defend a proposal into the Senate universities. And then after that, the proposal went to JPU, the top level management who evaluate the proposal. After that, so the proposal will from JPU will be sent to higher education in KL, in Kuala Lumpur. Okay, it took us about 9 months to do all this. So again, during the process of the evaluation, okay, so they want to see on how on the data actually. And in my era, okay, it is easy for me because the previous 4 head of lab has designed the system. Okay, so this committee, they want to see the data. Okay, the data, all right? The data, how many consultancy that you have done so far? Okay, this is the example that I have shown them, the summarize of that. Okay, we have generated about 1.6 million ringgit, okay, from 2009 until 2019, okay. Those are the companies who came to us. And then they also want to see how much research grant, publication that you have from Ministry of Education, from Ministry of Science, from contract research. They want to see the data like this. is going up every day, every year. They want to see the publication, how much you have publication. Okay, since we are on the experimental base, our ISI paper are considerably okay. Okay, so we will work harder to have more and more publication. Okay, these are the kind of the information that they want to see. Also, how many per year postgraduate student, PG student, ongoing, and graduated student. Okay, when they say graduated student, is the student who already passed the viva and so on. Okay, these are the data that we have to show. And then at one stage they want to see, they want me to show how many current research that you have, active research grant that you get from UTM, from ministry, or from international. I'm lucky at that time because Professor Wan Karuden got a 3.8 million, something like that. So that add on to be, the sum altogether will be 5.3 million plus. Okay, the rest are contribution from colleagues, from department. Not me, this is not my data alone. Okay, this is my colleagues' data. And then Prof. Shohaimi got 500,000 for the, I'm talking about the data. Okay, because they want to see there's something facts and figures like this. Okay, how many ISI that you have, how many scopus that you have, how many grant research and so on come to you. Okay, so then how many collaboration that you have with local and international university? This is I shown to them. Okay, University of Glasgow in France. Okay, of course, BPPT from Jakarta, Cambridge, and so on. Okay, these are the list of our friends, collaborator. We have 23, all of them. We want more, okay, in the future. So, and then as shown by Professor Anton just now, what is your 5 years strategic plan? So the strategic plan is by the year 2024, we are financially sustainability. Okay, we are financial sustainability. This is core business. Okay, the core business that we have. All right, core business still on academic. Okay, we are still on academic research. Okay, testings. Then the roadmap that we designed, okay, for AeroLab must be aligned with the strategic roadmap of the university. Okay, so we have to be aligned with the research, publication, and DNA of UTM. Okay, and how can it cannot go? So they asked me also, what is your plan in the next 30 or 40 years? So I mentioned to them my third phase is from 2028 until 2037. Of course, that time is not me anymore. It's going to be my juniors here. We are the game changer. We are game changer in the world. We hope that's why you need more and more friends. All right, someone have asked me to go faster. All right, so then finally we've been awarded as a Center of Excellence by Ministry of Education on the 3rd of December last year. So now I want to share our 4 years work headed by Professor Wan Karuden, okay, on how to get the accreditation, how to get ISO 17025, okay. It is like for a professional man in how to get IR for you, okay, how to get IR. So ISO on how to get IR for your lab. I'm very sure all lab have that facility, having that equipment, but the most the difficult part is on how to do the documentation of your lab to be accredited. So okay, so we are applying we are applying ISO 17025 actually 17025. So the process of accreditation is not easy. It's not easy process. Okay, it goes to submit application, then it come to adequacy audit, it come to pre-assessment compliance audit, it come to assessment report, and then accredited awarded for a period of three years. So within these 3 years, we have to show them documentations, filings, and so on that for us to maintain the ISO 17025. Then we are thankful to university for providing some financial for us to maintain this ISO 17025. Okay, these are the elements. So these are the element of document that you have to prepare. Okay, while during the process of ISO 17025, so sampling procedures, testing report procedures, quality procedures, test compliance, test calibration, customer procedures, all are documentation. As I mentioned to you just now, to every lab in Malaysia or in ASEAN, you have the capability, you have the things to get ISO. But the most difficult part is to get it done in the documentation point of view. Okay, some on how to manage. Okay, on how to manage the ISO 17025. Okay, on how to maintain it is clear on web page. Okay, so we have to follow that. So this is the stage that we've gone through from year 1, year 2, year 3, and year 4, and we have to go through every year in the future because to maintain this ISO 17025. For your information, for international participants, UTM is one of the research university together with UPM, UKM, USM. Okay, there are several criteria to be a research university. One of them is accredited lab. So we must have, every university must have 5 at least accredited lab. So we are okay. No? We are okay. So some of the elements that we have to maintain as a director, okay, good manufacturing and laboratory practice, okay. All of them are the what? We call it as the documentation that we have gone through. And then we need a scope of testing. What are the things that you want to prove that is on a standard to be granted as ISO 17025. So the test that we choose at that time was aluminum.
Can you make it faster?
Okay, no, in 1 minute, okay. So then, okay, there is the certificates that we get early this year, 16th of February, that we are one of them. Okay, this is the this is the what do you call it, logo, which the accredited numbers, very nice number, SAM 1001. Okay. So that's it. How to go forward here in Aerolab is on how to survive. Okay, how to survive to get research grant and publication and consultation. So that's why I organized this conference. So we plan to do that yearly. It's not organized by UTM alone. We may propose next year. We may invite local university, UPM colleagues, okay, BBPT in Indonesia, ITB to join as a collaboration to organize that. So then we will go together. Okay, thank you. So it took me about 20 minutes. All right, thank you very much for your kind attention to my colleagues and so on. We will discuss further on how to organize this conference, which more organizer around ASEAN. Okay, with that, thank you very much, and Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi. Thank you very much, Dr. Shabuddin. I think I will not drag it further. Can we just open for a couple of questions? Thank you very much. For all 5 of them, should you have any question? If there are any questions from the others.
Thank you again for the previous head of lab, okay, for make my work easier. And also the support from local universities here. We are in a small community. We cannot run away. UPM, UKM, BBPT, UIM. Sorry, sorry. All right, sorry. Yeah, International Islamic University. Okay, UPNM. Okay, all right.
I have a question.
Yes, Hanafi, please, thank you.
Yeah, first of all, congratulations UTM Aerolab for your 20th anniversary. Congrats, that's more than achievement. Do you open for research fellow for Aerolab? Because it looks interesting that you build your own people in one lab, Aerolab. So you go with the lab, you not go with the department. You brand yourself Aerolab. So do you open for research affiliate or a fellow for your lab? Thank you.
Actually, we are very much welcome those who want to do a research fellow at our place. Actually, please come. Please come. Okay, because UTM also provide a limited place of postdoc and also research fellow. So if I'm not mistaken, this year they will announce the program, call for research fellow and postdoc students. Okay, we do that and answer that we do that.
Are there
no
any
charge
questions from others?
I can give a comment, please.
Yeah.
Yes.
Yeah, Panton, is it?
Yes, thank you.
Yes, Prof. Silakan.
After 5 head of laboratory from Engineer Care, Prof. Nasri, Prof. Suhaimi, Prof. Van Khairuddin, and Dr. Sabuddin, I'm very proud with the achievement. Such every period of time, different challenges, but you can manage it. So this is more art than science, actually, to manage people, because good a business can be sustained. There are 3 things have to be developed: the teamwork, the quality work, and the network. So all those things I already saw from the beginning, starting from Pakir to Sabuddin. So this is just maintain the spirit, have the quality work with the quality internal, of course, but the people behind is very important. And then teamwork just already built up very good. And then finally networking, because it will generate revenue through networking. So the people said silaturahmi is creating more risky for you. So that's very important. That's why in the future, the collaboration with the broader society, I think is very important. That is my comment on it. Thank you very much.
Thank you very much, Dr. Anton. Are there any other questions or comments to raise before we close the session?
Maybe one comment from local university, local colleagues. Okay, welcome.
Assalamualaikum, Chairman.
Yes, Prof. Rahim.
Okay.
Assalamualaikum, Prof.
Prof. Rahim.
Okay, after hearing the presentation keynotes from beginning until the last, Dr. Shabuddin to handle the lab, I think it is quite impressive, and I would like to congratulate the team, Aerolab team, and happy anniversary, happy 20th anniversary. So there's a long, maybe another 20 years ahead. There will be a lot of other challenges.
Yes.
And probably it's also a very good idea by Dr. Shabuddin just now that Aerolab is opening up to other friends and colleagues from other local university. I believe it can benefit not just UTM, it also benefits the nation. Then inshallah, we at UPM especially will contribute and participate in all activities organized by UTM Lab. So all the best.
Thank you, Prof.
Thank you very much for your comments, Prof. Rahim. Any other comments or other questions? Thank you. Right. If there are no comments, and I know that we are running late and lunch is probably waiting in front of you, in the afternoon, we have got 5 parallel sessions, depending on the areas of specialization or areas of interest with respect to the papers. We have already allocated the papers into 5 different rooms. And I believe that you have all the information already sent to you via WhatsApp and also on the web page. And we will start again at 2 o'clock. And I believe that the chairman, the host, will want to start exactly at 2 o'clock. So please, be punctual, and we hope that we can start our session and finish all the presentations by 5 o'clock today, inshallah. So we start at 2 and finish by 5.
Want to do photo or not? No? We have time today, now?
I think we already had, okay. If you can, while we are together, can we have another group photo for everybody?
Everybody, yes. Please switch on
Because
the
this morning
camera.
we have less people. Now we have more people. Can we have everybody switch on your cameras? Thank you. The only thing is Dr. Shabuddin's camera cannot be switched on.
Oh, that's always. It's switch on now.
Yes, but we cannot see you.
Amalina gitu. Amalina ada?
Yes, Amalina ada. Amalina will present this afternoon. Like we fire him to this afternoon.
And no, my student will present.
I see. Let you be prepared, Bilal. We will be fire you. Sorry. Joking to you, Bilal.
Okay, I'm taking the second page now. Everybody, can you switch on the cameras? Thank you.
Nice to see you all here today. Thank you so much, everyone.
Yes.
Okay.
Not yet. I'm going to the third page. We've got 3 pages.
Prof. Anton, apa kabar?
Baik. Terima kasih.
Dah lapar, I know.
Lapar semua. Thank you, Prof. Pakar, for joining since the morning.
Okay,
Thank you, Prof. Zaini, from the morning.
No problem.
Okay, nanti kita
Congratulations
dapat
and happy birthday to Aerolab.
Success.
Apologies me if I don't mention your name.
It's okay, no problem.
During my talk.
No big issues.
All right, thank you very much, everyone.
Okay.
See you again at 2 o'clock in the respective rooms.
Bye-bye. See you all later.
Assalamualaikum and good afternoon.
Bye-bye.
See you guys later.
Thank you.
Thank you. Bye-bye.